Good morning. One of the most interesting things that we can observe.
Now can you hear me? Thank you. Good morning and welcome to the 2024 AMSAT Colloquium. I'm Dave Johnson. I'm the Honorary Secretary of AMSAT-UK, and along with my colleagues who set up this event for the next 2 days, I'm very grateful. It's going to be an interesting set of lectures, and the first one we have is from our chairman, Professor Sir Martin Sweeting, to give a presentation about what Surrey Satellite Technology and SSC are up to, and some of the things that AMSAT-UK are up to as well. Okay, Kieran.
Good morning and welcome to the 37th AMSAT-UK Colloquium. I'm really sorry I can't be with you yet again this year because I'm attending the International Astronautics Congress in Milan. But let's first of all have a quick look at some of the things that have been happening since we last met. One of the most interesting things that we can observe is the huge number of satellites that have been launched. You can see from this graph how since about 2020 we've seen an almost exponential increase in the numbers of satellites launched. This, of course, has been dominated by the US SpaceX Starlink constellation, with nearly 6,500 by now satellites having been launched up till July of this year, but also the satellites for the European OneWeb and China's Guohang and Xing G60 constellations. And all of this means that space debris is a serious concern, and we're now having increasing awareness about the space domain and the environment and how to preserve it. The huge increase that we've seen in the numbers of satellites launched in recent years is largely due to small satellites that have really changed the game in the space industry. They've enabled many new entrants into space because of the lower cost, the shorter timescales, and the more modest facilities that are required to produce them, and yet they produce useful capabilities because they've become increasingly sophisticated. When we look at the numbers of satellites launched in the last few, even in 2022, see 97% of all those spacecraft launched were small satellites. So it really has changed the game for space. The popularity of small satellites is really evident when you go and attend some of the conferences. I went to the very first Utah SmallSat conference. I think it was in 1987. There were about 30 people in a small room, and it was considered a pretty, fringe and hippie event. Now, fast forward to 2024, and at the 38th SmallSat conference, there were over 3,700 people from 44 different countries. But as I mentioned, this increased number of small satellites increases space debris, increases the risk of collision. And in fact, we have a very special interest in collisions in space because in 1996, the very first documented collision between a spacecraft and a piece of debris where the spacecraft lived to tell the tale was with our Ceres satellite, where a piece of debris severed the stabilization boom. We were able to recover the satellite, identify the piece of debris which was left over from a spent Ariane rocket. So in the last several years, we've really been concentrating on how we can help reduce space debris. That is, by not creating it in the first place at the end of the useful life of spacecraft, deploying a mechanism such as a sail that you see demonstrated here, which will cause the spacecraft to have increased drag and then bring it down to re-enter and burn up in the atmosphere, thus removing it from orbit and the potential for creating more space debris. Of course, that's fine if your satellite is equipped with a deployable sail at the end of its life. But of course, many pieces of space debris or dead satellites are uncooperative. And so in 2018, we demonstrated through the mission called Remove Debris, two mechanisms where we could remove pieces of uncooperative space debris. Now, for small pieces of debris, we use net deployed from the satellite to capture the piece of debris, pull it back in, and then bring it back down into the Earth's atmosphere. For larger items where a net would not really be feasible, we deployed again the Roman technique of a harpoon, and the harpoon would lodge into the spacecraft, and then we could again bring it back down in to re-enter in the Earth's atmosphere. Videos of exactly this happening. So on the Remove Debris spacecraft, we took our own piece of space debris, a small nanosatellite, ejected it from the mothership, and then deployed the net, which you can see here on the right, to capture it. And then later, using a target deployed at the end of a boom, then use the trident, if you like, to then spear it on the end, and of course luckily keep there. So these are demonstrations of how we could use techniques to remove pieces of uncooperative space debris. This was all videoed from the mothership. Actually a pretty busy year. We worked together with the European Space Agency and the Japanese Space Agency JAXA on a very complex instrument which contributed to the EarthCare mission. This was launched on a Falcon launcher in July, and you can see the large spacecraft being deployed from Falcon, and then the medium wave infrared instrument that was carried, constructed at SSTL on board for climate monitoring. Recently, just a month or so ago now, was the launch of the first satellite for the UK Space Command. So this is the first UK sovereign intelligence and information gathering spacecraft for MOD. This also was launched on Falcon amongst a whole range of other small satellites you can see on the launcher here in the middle. The satellite has optical cameras on board, and this spacecraft is just going through its final commissioning before we hand it over to the MOD customer. Well, the next 2 years are going to be similarly rather busy. We have 9 spacecraft currently being manufactured, 2 for satellite view taking infrared images, satellite for Thailand, another demonstration mission of radar, a radar mission for the Norwegian government, a training program, an Earth observation satellite with the Philippines. We have our lunar mission, which is under construction at the moment, and 2 spacecraft, the European Space Agency using GNSS reflectometry for climate change and hydrological variables. So that is a quick snapshot of recent activities worldwide, and also, of course, here at Surrey in SSTL. I'm sorry I'm not going to be with you, but I hope that you will have a very entertaining, a very informative, and a very enjoyable colloquium. And hopefully I might see you next year.
Thank you, Martin. We're getting sound? Yes, we are. Martin Sweeting and I are of the same vintage. We've been around the space industry for about the same length of time. Of course, Martin's been doing it professionally. I've been doing it as an amateur radio operator. And some of my friends in the audience will laugh at when I say I've retired about 4 times. I keep coming back into the industry, and I'm fortunate now that I actually work for Goonhilly Earth Station as a software engineer. Amateur satellites have done an awful lot in my life, and talked to a lot of students, STEM outreach, and they always ask the question, how do I get into space? And we say, join AMSAT, join the other organisations, go to university, join the amateur radio clubs there. And there's always opportunities. The space industry in the UK is desperately short of engineers. So any youngsters watching out there, please consider the space industry as an option. I'm pleased to hand over to our next speaker. Heather, would you care to come up? We're going to be a slight changeover of laptop. Is Heather Nichols. I've got to, of course, get the get the call sign right, M0HMO, and she's going to talk about getting started in amateur satellites.
Okay. Right. Well, yes. Thanks for inviting me, guys. It's yes. I've given this talk a few times. Hopefully, you'll find something new. It's not as well prepared as I would like, because Thursday night, when I was going to write the talk, this thing happened. So anyway, let's get on with some amateur satellite stuff. So what's up there? I don't know whether anyone here is particularly new to the subject. Hopefully, okay, yep, good. So there's some people who are going to benefit from this then. So they've got all technical names, but basically we've got some flying repeaters where you can talk to them, and then they give out the same signal back down, and so as it flies overhead, you can talk to other people through that way. We've got some technical stuff where the satellites are transmitting data. Usually it's about the flight path, so when it's in light, what the battery voltage is, all that sort of thing. Then we've got the ISS. Hopefully you've all heard of the ISS, which does lots of useful amateur stuff. And weather satellites getting weather imagery. It's not quite AMSAT kind of thing, but it's working satellites anyway. And finally, we'll talk a bit about Oscar 100, which is the geostationary satellite. So I'm gonna whiz through some of this. So the first problem people have is these things are up in the sky, and mostly they're moving quite fast. So you need to be able to find them, and you need to be able to work out where they're going to be so that you can work them. The default sort of go-to place to find out what satellites are up there is this page, the AMSAT status page, and basically this just lists all the currently interesting amateur satellite workable stations. I think yesterday there were 32 on the list, so there's plenty of them up there, and so you can see the ones in blue are active. So the ISS is doing data stuff, and AO73, there's SO50 as well, which isn't on that list. But so there's plenty up there to go and find. Once you've picked a satellite that you want to work, and you can see from this diagram that it's actually doing stuff, and other people are working it, then you need to find out about its orbit. There are plenty of websites. Just search kind of satellite and orbit, you'll find one. This is just one I use quite a lot, n2yo.com. It gives you this sort of picture. I think we've got so here's a zoom in of it. So it shows you the orbit and because of the map projection, obviously it's going round in a circle round the Earth, but because of the orbit and the map projection, you actually see it as this wavy line sine curve. And also, of course, the satellite isn't that high up, so it doesn't shine on the whole of the part of the Earth that it sees. It only shines on a bit, and that's what the circle around the satellite is. So everything inside that pinkish circle can see it and have radio communications with it. So that's called the footprint, and the path obviously is useful. So you can see that particular, that's the ISS, it's a while ago. That one is not quite going to be workable when it comes up to Europe. But again, be aware that that footprint will change because of the map projection. It won't always be a little circle. As it gets up further north, it'll turn into an oval or whatever. So yeah, map projections do cause a bit of trouble. Also, if you get quite advanced in this, you're going to want to be able to track the Doppler. We'll talk a little bit more about Doppler. This is a little program by a guy called David Taylor, WXSat, WX-Track, which lets you connect up to your radios, and if you've got a radio that can do cat control, it will handle all the frequency problems for you for Doppler, but we'll come back to that in a moment. Okay, so I mentioned these flying repeaters, FM transponders. Like I said, there's loads up there. I got a soft spot for SO50. I did quite a bit of working on that a while back. And everybody's got them up there. There's one on the ISS, there's China, there's Saudi, Americans, there's lots of them up there. Antennas to use, well, yeah, let's make your own. This is my favourite little prop. So a bit of wood, a couple of bent coat hangers and a couple of bits of wire, and you can make yourself a 270 antenna. Very, very cheap, I guess. I didn't pay anything for it. You need to make a little diplexer, that's this thing here, which has sadly fallen apart in the car today. But again, there are plenty of designs online. Most people will do this sort of thing, or you can buy the elk or the arrow antennas. We were going to have them here, but we haven't, unfortunately. They all require that you hold the antenna and point it. So I had this great invention. I made the handle longer so that you can put it against your hip, and then you can move it around and you don't have to take all the weight on your wrist. So there you go. That's a simple thing that you could do. We'll talk a little bit more about that in a moment. But yeah, so you can go and buy them. They're not all that expensive. Or you can make your own, and there are plenty out there. Kent Britton, who's one of the keen, well, he's a anything microwave guy from America. He often comes over to the club. I don't think he's here today. He's done quite a bit on designing these things and optimizing them. So, does anyone not know what Doppler is? Okay, so I can skip over that. Often I give that in clubs and they say, "Oh, what's Doppler?" And then I end up having to do train impressions. It's not a good thing. Anyway, so we've got to correct for the Doppler, and it's not big for these satellites, but it's enough to put an FM receiver off. So how does this sort of thing work? Here we go. So you need a good radio. I have heard that people have worked these satellites on Baofengs, but a decent handy, that's a Yaesu handy, will do the job. We've talked about the diplexer, that you can buy them, but you can make them. And the only other thing you need is a CTC SS tone. So how do you work them? Well, you use one of those programs to work out where it's going to be in the sky. So for instance, if you know it's going to come up over there, it's going to go up to maximum altitude over here, elevation angle, and go down over there, and it's going to take 10 minutes to do it, then you know it's going to be there at 5, there at 2.5, and so on. So you can get in your mind a picture of where it's going to be at what time. Then the trick is to have. Yeah, I'm going to have to put the microphone down. I'll demonstrate this. Okay, I'll shout. So you've got your radio hooked up like so, and on the radio you've got a tuning button so you can change the frequency slightly, as you know with the Doppler. So when it's coming towards you, you're going to see a higher frequency than when it's going away from you, so you need to bear that in mind. And we'll show you some of that in a minute. So you start off over here, you're listening to your radio, you hear something, you turn it to get the best polarization. You move around as you keep an eye on time, get your watch on your wrist. And as it goes round, you should be able to track it, keeping an eye on the frequency and on the polarization. Recommend that you do a couple of passes without actually using the radio to get the hang of it, to listen to see how people are doing. These things happen quite quickly. It's usually sort of someone calls CQ, someone goes back to them, they give you a report, you give them a report, and that's it, and they move on to someone else, because you only get a few minutes to do these the whole pass. So there's quite a lot going on. You're looking at your watch, you're looking at the radio, you're looking at the polarization, and you're trying to track where it is in the sky. So but it's very rewarding when it works. It's not like you just called CQ and someone came back to you. You have to work to get these QSOs. Luckily, there's another AMSAT page, Beginners How to Work the FM Satellites. It has a recommended set of frequencies, so those are the ones that you want to program up. You're going up on 2 meters, down on 70 sems, and that gives you the Dopplers. So you only correct one of them. The satellite will handle the rest of it effectively, and that's it. So you know where it is, you've got the tuning, you're working it around, and eventually you can have the QSO, and it's quite good to get that. Okay, there's more than one of them. Okay, so let's have a look at the ISS. Lots of things going on up there. APRS, for those who like to do tracking. You can bounce your tracking signals off the APRS transponder up there. You've got another one of these voice things when it's on, and occasionally they do SSTV, which is quite rewarding. Again, you can usually get an entire picture or a picture and a half in a pass. So that means mostly at the moment it's been the Russians have been doing SSTV, but we have had some American ones, usually celebrating some event. Antennas, you don't need to worry about this sort of thing. Very, very simple. If you've got a cell phone with what have I got there? Robot 36. I use Droid SSTV on my Android phone. Put the speaker of your handy somewhere near your microphone on your Android phone, and roughly get the signal, and you'll probably get a picture out of it. So it is that simple. If you want to go up a bit of a notch in quality, collinear on the roof. I've done it from the collinear on my car. I've got a white stick on my chimney, like most people, and these will all get good pictures down from the ISS. What radio? The little RTL blue dongles. I don't know if everyone's familiar with these things. They're TV adapters. You can get them on eBay. I think they're about 20 quid these days. Or if you want to, I don't think I've got mine here. There's a silver version of it, which is a little bit more expensive but a little bit better. Or you can go up to one of these RSP SDR Play things. They're 150 pounds. I picked that one up for a tenner at a radio show. And they do a great job as well, so I'd highly recommend any of those. And as I said, the handy for doing pictures is quite fun. There's a little plot I got of things going on from the via the ISS for the APRS. You can see I was working on the list there. And of course, it's got a big footprint, so you can see people, a lot more people than you would normally get in your normal zone of an APRS 2 meter. There's a picture I got, so as you can see, reasonably high quality. That's one of the better ones, but yeah, you can get some pictures. If you get plenty of pictures, Aris will send you a little award. So if you're an award chaser, there's one from space. That was 2017 as well, I think. Okay, SAO, the Oscar 100. So this is a different beast. This was a game changer for AMSAT, really. It's a geostationary, so it doesn't move, but it is quite high frequency, as I said, 10 gigahertz down, 2.4 up. Now, the reason they picked 10 gig down was that you can use a standard satellite receiver dish and a standard LMB, and you can actually receive this. So if you've got an old Sky dish with a Sky LMB, it probably will do the job. It might not be great, but it will get you started. If you have a look downstairs in the AMSAT thing, we've got a rusty old dish. I don't say the rustier the better. Well, actually, I probably do. But it's up there, and you can use that size of dish. So it is more challenging. It has a narrowband transponder, so you can do voice. It's okay with the right bits of software. It's better. But you can also get into the amateur TV. BATC have worked very hard with these guys to get a lot of TV stuff going. We'll talk a little bit about that. So the challenge of finding things here, you don't have to worry about finding the satellite. It doesn't move, so you just have to point your dish in the right direction. You do need to worry about where to go on the band. So this is a band plan. On the left-hand side, you've got the big beacon, which is a 2 megasymbol beacon. So it's basically just all the time it's transmitting TV pictures. And then on the right-hand side, you've got various people using the narrower TV signals. And you can see there's lots of gaps that you could just pick a gap. Over on the right-hand side of this screen, there's a chat room. You can go into the chat room and say, oh, I'm going to pop up here and I'm going to be using this type of TV and this modulation and so on, because there's all sorts of different options. So that's the way people can find you, and you can have a QSO, a video TV QSO. So receiving it, as I said, Sky Dish, 10 gigahertz horn will work for those doing microwave stuff, but most people are just using a normal dish with a decent LMB. If you want to do receive only, those little RTL SDRs, they're not great, but they do work. You can hear the QSOs. The ATV receiving these pictures, you need to build yourself one of these mini tuner hardware. So if you are interested in that, go on the BATC website, or downstairs they've got a great setup down there with demonstration. I think it's all running. I'll look at Joan to see if she says yes, it is. Yeah, so everything's going downstairs. So yeah, if you are interested, take a look at that, and the BATC will sell you all the kit. It's an easy kit to make, and you can start receiving TV pictures very, very quickly with just very simple hardware. Astra LMBs, as I said, you do need to get a bias T in there if you want to transmit. Now, actually, you want the bias T anyway, because you need to power the LMB. So that's just a little expense, and again, the AMSAT or BATC will sell you a little kit, one of those. Receiving it, TV, you can do from PC or Raspberry Pi. There's one over there. And I recommend a program called SDR Console. It's a little bit hard to get into, but it can make really good improvement to tracking the signals to make sure that they don't wave around, drift around with temperature and so on. Basically on a PC or on your radio, if you're doing narrowband stuff, the LMB comes out at 700 odd megahertz. So if you've got a radio that can receive in that area. Most SDRs will. You can pick up the SSB or CW for those of you want to bash the metal together. Okay, so transmitting is harder. No two ways about it. You need an antenna that can transmit on 2.4 gigahertz. You need a bigger dish if you want to transmit TV pictures. The little sky dishes aren't really up to it, but a 1 meter dish will do the job if you've got enough power. This thing called the Potty Patch of the Year, great little invention. It makes life very simple. It's 2 discs, goes on front of the LMB, and then it'll give you the 2.4 transmit as well as the receive. Radios, again, you're in a bit more difficult territory here, but any up converter, there are plenty available on the market now. Or you can use the Plutos or the Limes for those who've got those, and it works. You just have to get set up with a bit of power to transmit, and you can see your own signals. Okay, again, transmitting, if you want to transmit TV, the port's down, which is a Raspberry Pi based thing. It's a bit more complicated again, but it's easy to do, and there's so much support. The BATC have lots and lots of resources, so again, you can do good stuff there. You're going to need an amplifier for voice. One of these little Wi-Fi amplifiers, very easy to mod it up to do your job, and that's all you need. Just feed that Wi-Fi signal, or the signal out of that Wi-Fi amplifier, because Wi-Fi is 2.4 gig, of course. Just feed that into your Patch of the Year antenna, and you will see your own signals. These are I don't know what they cost. They're 20 or 30 pounds, something like that, from China. Okay. Yeah, I'll just say it's very rewarding. When you first get Oscar 100 and you receive stuff from it, it's a real buzz, because you do, again, you have to work at it a bit, but it's doable. Okay, we'll talk a little bit about these telemetry sats. So lots of things. The FunCube is a AMSAT project. In fact, I think all 3 of those are. Are they still up there? Does anyone know if? Because I think, yeah, I remember there was some concern about 1 or 2 of them not being there anymore. But anyway, so there's a lot up there. They all receive different types of information, and again, your white stick on the roof or a collinear on your car will do the job. The SDRs, I've used that blue SDR. I think it's say 20 quid's worth. It's hardly worth worrying about. GNU radio, GR satellite for Linux on the Raspberry Pi or PC, or plenty of other bits of software. Again, everything's online. Go have a look, trawl around the AMSAT website to find out what you need. There's a couple of pictures. These things are 100 by 100 by 100. They're about yay size, and they're hurtling around up there. Yeah, they seem to be very reliable, very easy to get. This is one of the dashboards, so this is a bit of software that's going to receive the telemetry. Obviously, it's not going to be something easy that you can read with your ears. You're going to need a PC. Feed it through the sound card. You get something like this. This is an eye diagram for those who are familiar with that. It just basically shows how precisely you are tuned in, locked into the signal. And that's the sort of information you get. It's a bit cluttered, but there's a bit about the power amplifier, about the what the various receivers are doing, and voltages somewhere, and temperatures, just generally interesting stuff. But the great thing about FunCube is that when you receive some of this, you're receiving just a little snapshot. But there's a thing called the data warehouse, where you can put all this data up to a central server, and it collects everybody's data. So you pretty much got a perfect record of all the transmissions anywhere in the world, anywhere around the world, from the past 10 years. It's been up nearly 11 years. So that is an incredible resource. And people are always being asked, if you're interested, come and have a look at the data, because there's a lot of data mining that people could get into if you're interested in that aspect of it, about all the sort of the temperatures and so on, and basically just the life cycle of 10 years of a satellite and what it does, what it can do. So that's a bit of citizen science. Again, it's very easy. The software you download just has a button to say, are you happy to upload this? And you say yes, and off it goes. And there's another one. I think that's, is that FunCube? I'm not sure. Anyway, that's the information that it's giving you. So it's all very similar. And again, if you upload some data, you can get a little certificate. So again, if you're a certificate chaser, that's another one from space. And yeah, the FunCube guys even give you a QSL card, so you can have a I received from space QSL card. Okay, we'll talk briefly about the weather satellites. There's a lot of them up there. The NOAA ones are the interestingly easy one to get. They're FM. They're just a little bit below the 2 meter band, so with a 2 meter antenna, again collinear, you can go get those. But you can do some interesting stuff with some other antennas. These are circularly polarized. It's easy for me to say. So it's not quite as easy as just putting up a dipole or whatever. But turnstiles, QFHs, they're all quite easy to make. If you go downstairs and have a look at the AMSAT stuff, there's some examples of some homemade bits of copper heating pipe bent into circles. Or the horizontal V, just a thing about this size, made out of a coat hanger. Again, the blue dongles do fine, and there's loads of software online. This is a lovely little thing. A bit of wood, a chocolate block, and a bit of coat hanger, and you can make up a little antenna. I like to show this slide. We were at an event a couple of years ago, and this guy Mark Phelan came up to me, and I was doing a demonstration with weather satellites, and we had a mobile mast, and he said, "Oh, I just built one of these little antennas. Can I try it out?" And I thought, yeah, this is great. So we put his little antenna up on the mast, and we got that picture. It's not great, but this guy had just seen us doing this, gone online, found that earlier antenna and made it with a couple of bits of wire, and that was really inspiring. It's really great when people can spend literally 5 minutes doing something and get some pictures like that. So I mean, the trouble is, you do that, you get hooked, you want to do something better, so you wire up to your collinear on the roof, and instead of having QSOs with someone next door, you download some weather pictures. For those who know, collinears are donut-shaped radiation patterns, so there's not very much received above them. So when it goes overhead, you get a fuzzy line where the reception isn't so good. The colours are kind of false colours, so the software puts on the grid, obviously, and the outline of the countries. But even without that, you can still see the countries on the display, and obviously you've got all your weather patterns, so that can be quite rewarding. There's a picture of a turnstile and this double cross antenna. I've never made one, but apparently they work quite well. The thing about the QFHs, these weird curly things, and also turnstiles, is they receive in the whole hemisphere. So you don't have to move them, you just put them up and they receive in the half of the sphere above them. So the satellite comes over the horizon. Yeah, thanks. Sorry, yes, okay. Yeah, and then if you want to get that little extra bit, because you want to overcome that little fuzzy bit in the middle, these guys, they're a little bit more than that now, but the Sawbird, they're basically a filter and an amplifier. You can just grab one of those, plug it in line. It's a USB powered thing, and that gives you something like that, which was with a QFH with an amplifier. Yeah, very rewarding and quite pleasing. And that is that's the end of that. As I said, most of this lot is on demonstration downstairs. The AMSAT stand, the BATC stand can show you everything you'd like to do. And there's an Oscar 100 receiving station. I think, is it transmitting as well? Yeah, yeah. So yeah, so you could go downstairs and have a QSO on a satellite right now if you wanted to. Thank you very much. Any questions? Do we need to give you a microphone? Oh, there we go. There's one there.
Thank you very much for a very interesting talk. Just wondering if there's anything equivalent to Oscar 100 over the Pacific, and if not, whether you know if there's any plans to make.
You'll need to ask somebody else. Anybody? I don't think there is at the moment. No. It's one of those kind of weird things that obviously the Qatari people wanted it to be over them, and that does preclude them being over America. So, but I'm sure there are plans. I don't know. You read about these things all the time, but so at the moment, no. But that said, come back later because there is some people. Where did you get to? North America did actually get into the satellite. There's a talk on that sometime later today, I think. Next session. There we go. Okay, so stay for another 5 minutes, and you could hear about the. Okay, half an hour. Yeah. Any other questions? There's one over here. Sorry.
Hello there, that's better than me shouting. With weather satellites, obviously you can build a dipole, get an SDR receiver. What software in the PC would I need?
Okay, yeah, that's a good question. Have I got an answer to that one? Yeah, so this program, WX2IMG, works very well. It just listens to a sound card. So if you're using one of those little blue SDRs, you need a virtual audio cable, if you're familiar with that, just to get the audio from your USB into the receiving program. WX2IMG, it's another one of these really great, almost plug and play type of software. You do need to track the Doppler for the satellite, so that that little program I mentioned right near the beginning, WX track. Again, you just put in the frequencies, tell it which satellite you want to receive, and it will track the Doppler for you. And then this program will you'll just see the lines appearing on the screen as the satellite goes over.
Thank you.
There are, of course, everything else for the Raspberry Pi. There's this NOAA V2 thing actually is quite good. It can receive some other satellites as well, which do higher res images. So if you're a Raspberry Pi or a Linux fanatic, then that's a good way to go as well.
Satellites these days have the ones used to be in very high orbit. All those have passed and have this such. Used to be the Fuji Oscar ones and things were going.
So there's lots of different orbits at the moment. Most of these are LEOs, the telemetry type ones. I'm not sure what the weather satellite altitudes are. I think they're probably LEOs as well.
But in terms of QSOs, there's only these low orbit ones now left as such.
There aren't many. I don't think there are any elliptical orbit ones. Anybody else? No. Okay. Brilliant. Yeah. No. So yes, you from way back, there used to be the ones in the big elliptical orbits, which would be visible for a long time. But yeah, they don't seem to have any of those. But then Oscar 100 is way out because it's geostationary. It's
Yeah, hi, thank you. I was just going to say one thing on weather satellites I've been playing with is some software called SatDump,
right.
which is absolutely brilliant. It works really well with the dongles, works on Raspberry Pis, Linux and Windows, and it's all fully automated. You don't have to do anything. You just load the software, select the dongle, connect it to an outside aerial, select the satellites, off you go. It does all the tracking, does all the Doppler, does everything for you, and it's free.
Brilliant. There you go. What was that? sat dump. There we go. Okay, there's another one. Yeah, it's brilliant, and it's so as you say yourself, it's very easy to do, and very rewarding because you get pretty pictures from space. Okay, well, I think we've run out of time, so thanks very much, and we'll see hopefully some of you downstairs with the AMSAT or whatever.
Thank you, Heather. Can we get a round of applause, please? One thing I would add is there are a lot of Internet of Things satellites up there at the moment, transmitting on 433. And if you look up an application called TinyGS, it runs on an ESP32 out of the box, and you can get satellites up to about 2,500 miles away, just running on a white stick. So that's another one to look at. We're now having a break for about half an hour. Come back in at 10:45. The next one will be, as Heather said, it'll be a report on the operations of QO100 from North America. Thank you very much indeed for your attention. 20. I have the great pleasure now to introduce Rani Gopal and Graham Sherville to talk about their exploits in North America with QO100.
Yeah, thanks, Dave. I must not stand in front of the projector. Good morning. This is one of my photographs. I'm quite proud of this photograph. Everybody's heard of Signal Hill in Newfoundland? Yeah, where the signals, Marconi was listening, I think he was at this end, Marconi was listening to signals from Poldhu in Cornwall, which was the first time that the transatlantic had ever been crossed with RF. I think the tower there was built after he did it. I don't think it was that old. Anyway, that's a famous place, and you'll see more of it later. And David and myself, MRF and myself, were located just there. The house that you'll see more of was just there. So we weren't far away. When we arrived, though, we could never see the top of the hill because it was covered in fog. So that's a bit of location information. Take us back 2 years, precisely 2 years, I think, in this very room, when AMSAT-UK announced a challenge for QO100 operation in North America. We described in great detail how the footprint of QO100 is there, and that I think that white blip there is Newfoundland, or it may be the yellow bit, but it's about 50 miles away. And we said, well, microwaves can bounce and refract and whatever, so it must be possible, mustn't it? Go and do it, and we'll give a prize for the first person that does it, and TV and the rest. So that's where it all started 2 years ago, and then it all went fairly quiet. And then we discovered that people on the east were operating satellites operating through QO100 at below the nominal theoretical footprint. So that was the status up to the beginning of this year. And nothing had really happened in terms of Newfoundland, which is approximately 0.9 degrees below the QO100 horizon. So that's why we thought it was possible. So actually what happened, completely coincidentally, not organized at all, it turned out that there were sort of three groups who ended up going to Newfoundland in the same week, actually 10 days, I think. First was Gopan, who is here, and he went out, and we'll hear from him in a moment. Also, a couple of Canadians, Stefan and John. Stefan flew from Toronto, Winnipeg, and John drove from not quite so far away, but he drove a very long way with a big dish on the back of his car, back of his bakkie. David and Graham chose the easy route. We discovered at the beginning of the year that WestJet suddenly started to fly direct from Gatwick to St John's, Newfoundland. It was a new flight. It worked very well. It was about 5 hours out and 4 and 3/4 hours back. Terribly easy. 737, nothing fantastic about it. And that's actually what made us do it, I think, because the thought of transporting ourselves and a whole load of kit via Toronto or Halifax and it getting lost and whatever didn't seem very attractive. But being able to fly direct made it possible. And there was also, which I certainly didn't know, a Dutch group had built a beacon and sent it over to another Graham, VO1DZ, and this beacon had sat in his station for a couple of years unused, unfortunately, until we came out. So it would have been really good if he had been able to use it before, because we would have known an awful lot more than we did when we set off. So that's the background. We can talk about where it all started, the unknowns, the location, preparation. Yes, I think we'll talk through that. Contacts and some pretty pictures of St John's. So, yeah, that's where it all started, the QO100. That's me, actually. Sorry, I just realised that's me in this room talking about it 2 years ago. So there we are. There were the unknowns that we put up at that point. Would a normal QO100 station be sufficient? Could activity include DATV? Well, the answer is it could if you stayed there long enough, unfortunately, and we'll come back to that. As signals from the ground station will be relying on tropo ducting. Should you be on the beach, well, or higher up, or right at the top? I think we concluded. David, what did we conclude? The answer is yes, anywhere, really. Certainly we found signals strong on the top of Signal Hill once. They were strong for you on the beach, near enough the beach. Gopan, you were how high above the seawater level? 10 metres? Yeah, 10 metres. And the Canadians were about the same. Yeah, we're on the low cliff. So they were probably, we didn't do any analysis, but probably it worked better in different locations at different times, maybe. And what time of year? Well, you certainly don't want to go there before May, because it's quite cold, wet, windy, foggy in May, so it's only going to be worse earlier on. Don't know what it's like at this time of year, and I would say August would be a much better bet. And the last comment about the actual footprint, well, the creator of the footprint is sitting over there, so I will not comment about its accuracy, but I gather it's based on the theoretical footprint from that height, and does take into account the oblateness of the Earth, but not much else. Is that a fair summary? Okay, good. Thank you, Phil. So, the location of Gopan. That's Gopan. May I introduce Gopan, M0XUU?
Yeah, thanks, Graham. Morning, everyone. Name is Gopan, call sign M0XEU. I've got an Indian call, Victor Uniform 3 Hotel Papa Foxtrot. So as Graham just gave an overview, the idea started after seeing the 2022 challenge from Graham. But at that point in time, I was not thinking that I'll be going, but eventually it started. The idea came in towards the end of last year. Luckily, around the same time, my partner was also looking for a trip somewhere. So I somehow managed to get it to St. John's because there were quite a few trails that you can go around, walk. I know May was a bit early, but we still booked everything for May. From June, the prices are quite high compared to May, and that's the only reason why I've booked it in May. So we picked up a location on the southern side called Petty Harbour. Luckily, on Airbnb, we found a beautiful location. So that's the location which we choose. They had a patio outside, which was quite useful to set up the dish and other things. And it was right on the sea. That's a view from the road, looking to the place where we were staying. And this was slightly more. The elevation was -1 at that point compared to Signal Hill. That's a view from the road onto the horizon. And it's a small town, a village, where you can see boats going in and out of the harbor. And it was quiet at that time. We didn't have much of a noise or any other issues. So in terms of preparation, I was active on Q100 since I think June 2020. So I had all the setup which I was planning to carry. The main concern was on the dish, because I remember back in December 23, there was a station from Brazil went to Uruguay, and he was using a 60 centimeter dish and was talking about deep QSBs and fading and things like that. So I thought if I go with a 60 centimeter dish, I might still face it. So I wanted to have something which is slightly larger. So went with an 85 centimeter, and I also had a backup in St. John's through Graham, Victor Oscar 1 DZ, 1 meter dish, which eventually I didn't have to use it. So in order for me to pack this 80 centimeter dish, I had to cut it into 2 and then pack it on a IKEA case, cardboard case. Physically, the stability was there, so I didn't have any issues with retaining the shape of the dish. So that's the entire setup which I took. So you've got the 2 amplifiers. It's a 10-watt amplifier. That's a homebrewed transverter, which is a mix of up converter from DX Petrol and designed by David G0 Marov, the down converter. On to the right is a Pluto SDR. As a backup, and then bits and buffs. So I've got everything is GPS controlled, a helical feed with modified LNB. So that's the setup which I've used. I didn't have to use the Pluto SDR at St. John's. All the QSOs, everything was done on the analog transverter. that's all packed. So next I think we reached there around lunchtime on 8th. It was grey, overcast, raining. We got to the location just after 4 o'clock, I think. And that's a view the very next day. So I've managed to set up the dish and everything overnight, but didn't manage to get any signal at that night, at that time. So the very next day, you can still see the clouds, and there was no signal until around 8 o'clock. I could listen to a nearby satellite, because when I flew from here, I was planning to track a satellite which is nearby so that I can get close enough to Q100, the horizon, and then change the elevation. So I was able to receive that station here, and that was the initial setup. So they had some garden tool bench, which was a bit elevated. So I managed to get the dish on top of it, which means it had a clear view to the horizon. So that's just a receive setup. At around 9:30 local time, that's when I was still trying to see whether I can get hold of that beacon, the lower beacon. That's when on the waterfall, I started seeing a faint line. So after fine tuning, we started receiving the lower beacon. I don't know if I can play. It's a video. I'll just click it. That's a very first signal received at St. John's. So this is really happy at that point. At least I received, but I was too happy that by that time Graham and Frank, they came up with the 2.4 gigahertz beacon to my location, and then we started setting up that beacon to see whether that's still working or not. So we switched on the beacon for some time, and then after lunch we went out thinking that the satellite is there. I've managed to receive some signals. I should be able to work more stations in the evening and maybe work a pile up in the night. Got back around 5:30 and there were no signals. So I thought it was just because the deep QSP or fading effect. I waited, and then I called David, tried to figure out what's happening. Because at that time, there was no clouds, it was sunny, everything was perfect, but still there was no signal. So David told me that it could be something right at the horizon, which is blocking the whole thing. And or it could be the movement of the satellite itself. So we said, we'll try again next day. Unfortunately, I've planned for a trip the next day. So I knew that after half six, I won't be there until late evening. Till around 6:30, there was no signal. It's completely empty. And we went out for the whole day, came back around 7 o'clock, and that's the day when we had the strong auroras with rain and sleet. So no chance, there was no chance that I'll be able to work any station. So come Saturday, I know that I had only 2 more days to have the contact. So Saturday was the make or break day for me. So that's that evening, I think, on Friday. Oh, and that's the the maximum which I've received, 20.8 above SNR with my dish. You'll later on see that the bigger dish from John and Stefan, they managed to get up to 33 something. So that's a view from below of the two dishes. So that's the beacon, which we ran it for some time, and then I had to switch it off. And the other one was the dish which I've used. That's the evening on Friday. Again, yes, driving back to the location. That's actually sweet on Saturday, on Friday evening. Okay, so so on Saturday, although there was a plan to go out and meet the local hams who are meeting at one of the shopping centers, but I decided to stay back and give it a try. I knew that with my testing, the signals were really weak uplink from my end. So obviously I started with FT8. I was on phone with David and also with Nina. So we were trying, and I've asked David to give a CQ call, because I know if you start, if I start calling CQ on 540, there will be a big mess. So we decided we'll move up, we get a clear spot, and David started calling CQ. You can see the amount of try we had to do before we get to the final one, which is the Roger 73. So that was the first contact, and then slowly started picking up. So that's the setup. That's with the weather protection and all. I guess this is a video. Oh, it's playing. Okay. Yeah, I've muted the audio because it was the excitement. I didn't want to share. Yeah, so that's going on, and you can see me on phone with David. So later that night, we've gone to CW, and this is again from. Oops. So most of the contacts were, I had to go really slow because of my signal strength. It was really weak. So I think we worked almost 140 stations on CW. And then quite a few on FT8 as well. So the interesting thing was, at one point you'll have your entire spectrum filled up with stations calling you, and in like five minutes it'll be empty. There'll be absolutely nothing. So it was giving you a feeling like working on an HF band where you have deep QSPs, but yeah. So yeah, so that's the certificate from AMSAT, and that's Graham on the left. Next to Graham is John, V3 CMJ, I think, yeah, and Stefan, V4 Sierra Whiskey. So that's the QSL card which I've entered. I guess that's pretty much, and some shots from St. John's. It's a lovely place to visit. A bit expensive after May. Yes, yes. Okay, I think that's it. Thank you.
Okay, so carrying on, that was where the Canadians were. Gopam, where was that in relation to you? Were you further? You were up here slightly, were you? Oh, were they? Okay, there, fine. So a bit further south than we were. Not that that was terribly. And that was their view from their car park, V4SW. They obviously took that when the fog wasn't in, but most of the time they were like that. Certainly when David and I went over to see them one afternoon or morning maybe. And John had driven this vehicle, I don't know what you call it, bakkie, but not with the dish fully erected. Apparently they took it half to bits and then put the other half together on site every time. But a fairly difficult task they'd set themselves, and particularly when you can't see where it's pointing. But they got very good signals for some periods of time. But their operating conditions were not what I would call ideal. We chose the easier route. As I mentioned earlier, the on the map on the left here, Signal Hill is up at the top there, and Fort Amherst is down here, the other side of the entrance. That's the main shipping entrance into St. John's Harbour, and we were located just there. We were at the junior assistant lighthouse keeper's cottage, because that was chosen to be the one right on the edge. And like Gopam, we had a balcony as well. It was all carefully selected, carefully thought through. This it wasn't just thrown together at the last minute. That's another shot of the sort of entrance. Apparently, sometimes when you look out, you actually end up looking out at icebergs floating by. So a bit of preparation photographs. Like Gopam, we were worried about dishes and size of dishes and how big a dish you could get in the aircraft. I ended up, David and I took two completely separate sets of kit. David was primarily for FT8 and CW intended. Mine was intended for SSB and DATV. So there are various bits lying around here. I was trying to prove when this photograph was taken that with this dish, a 65 centimetre dish, I could actually receive the DATV beacon, which I could prove I did. But we were also playing around with transmitting via it, and that's the PA, the 200 watt PA there, and there are various bits of stuff all over the floor and chairs. So anyway, it was a nice sunny day. And another experiment that David and I did was to go off onto Dunstable Downs and see what beacons we could hear on 10 gig. Excuse me. Also, the intent there was to prove to ourselves that the dishes were actually pointing at the horizon, because obviously with the offset dishes you need to get them angled quite a long way down. You can see David's one there in the background, and you'd increase the projection off the pole, I think, and I'd done something similar on mine, drilling holes in the bracketry to get the down angle. And we did quite well up there. We heard a beacon over in the south, near the south coast. I can't remember where it was. I was very suspicious that we'd never hear it, but we did. Happiness there. Oh, sorry, pushing the bother. Yes, departure pictures look very similar, don't they? My one there. So I actually took two sets of kit in the luggage hold on the aircraft. The big kit with the aerial, mine was not cut in half, but you can't really make it out there. But there was carry-on baggage there, and I don't know, those of you who were here last year, over in the back corner, I had a demo station of QO100 with a small dish and a laptop and a box with a Pluto in it, and a PA. And that's what I took, is hand baggage, and a toothbrush, of course. But that was the equipment. Oh, and a 99-watt lithium battery. So I was working on the worst case, sort of backup redundancy, that if the baggage went missing, there wasn't another flight from Gatwick for 4 days. That was the flight we were going to go home on. So if we needed something that wasn't going to go missing. In the end, nothing went missing, but that was the plan. So yes, pictures of the assistant lighthouse keeper's cottage. You can see David's dishes there. You cut yours in half as well. Sorry. And that was joined together. That worked well. And my one, I think you see a bit later on. It's another picture of David's dish in the more normal weather. I realised actually afterwards, going through these photographs, that the Canadian flag is either blowing that way or it's blowing that way. And I think when conditions are good, it was blowing the other way, and when it was blowing this way, we never saw a signal. That's my theory. So yeah, we had a selection of dishes. David's one's down there. Not pointed to it. David went there on the balcony. The 1 metre dish that the Canadians had got for their beacon was sort of round the back. I just stuck my dish out the window on a small pole, which I brought with me. And that's the dish that you saw last year, the one that I hand carried, which was just on a sucker on the window. And yeah, it worked. Well, anyway. Yeah, there we are. So it's sort of the view out. Misty, cold. Oh, and the foghorn. Yes. I found sleeping with that foghorn going quite difficult. For some reason, I let David have the bedroom round the back. I don't know why I was so generous. But I think actually what woke me up on our last morning at about 5 o'clock. Excuse me. I woke up at about 5 o'clock and I don't know why. I think it was because the foghorn had stopped, because the mist or the fog had lifted, and that was when conditions were really, really good, just before we were leaving. Canadian beer, whatever. That was a picture of David's equipment with a very attractive looking Morse key. Did you actually use it, David? Once, okay, good. And we've heard Gopan talking about how weak the signals can be until the very last day when the band really opened up. Evidence of a weak signal in a waterfall. We've seen those before. I have to say, credit please to Simon G4ELI for his SDR console software. I found it easy to use, very convenient. You could leave the transmitter running and just in a quiet shack, all you did was talk to people and tune the band 10 kilohertz up and tune across. It didn't require push to talk or a box or anything. It was very easy and very enjoyable. Yes, that's what the band looked like on some occasions when it was busy. I say the band, QO100 looked like. Situation photographs. My shack was on the left there. Again. That goes back, doesn't it? Yeah, okay. So my shack was over there, and David's shack was there, and the fridge was just there. All that mattered, really. I think David must have taken that when I was really busy and trying to concentrate on quite a few signals there. is the signal as received.
Yeah, 57 QSB is saying here you disappeared completely there. GATVR, I'll give you 57 now. 57 on peak. So, okay, Ron, over.
Give credit to SV8.
Going QRT in 14 minutes, I'm afraid. VO1 oblique G3 QRZ.
Thank you to SV8DH oblique DH7 for sending me that video. Here's another one without audio, apparently. Bit weird. But you can see my signal there, or our signal, and then suddenly the band lights up. Not sure why there's no audio on that, because I was very loud, and I apologise. At one point we were hitting Lila, which is a cardinal sin, those of you who don't know QO100. If you activate Lila, your signal is over strength, and would you please turn it down? Yeah, so that's the beacon created by P1CMO and his group, which we tested and worked very well. We also went and did some socialising in bars and in McDonald's with some of the locals. They were very, very welcoming. The morning meeting, coffee morning, it's like the East Anglia group, isn't it? So 10:30 on a Friday, was it, I think? Something like that. David wanted to take me to show me the low life of. Not sure it was quite at that angle. The angle is very jaunty. I think the wall is vertical. So the Saturday came. We arrived on Wednesday night. We operated Thursday and Friday. Saturday came. Our flight was not till late on Saturday. We had some things to do, and we had to be out of the house by 11 o'clock on Saturday, which was an error. We should have had another day there. So when we were operating on Saturday morning, I'd woken up at 5 o'clock, switched on the radio, the band was full. I went and knocked up David and said, "Get up, get up, get up, get up. Don't worry about getting dressed, get up." And then we were panicking about getting everything de-rigged and off-site by, I think it was 11 o'clock. So that was why we were a bit distracted, and again, why I apologise why I never got the DATV kit from over there to over there and rigged it up. However, that morning the fog disappeared magically, and this is a photograph taken from very close to where you saw the first photograph of Signal Hill. This is the car park at the top of Signal Hill, or very close to the top, and out there is the North Atlantic, and the clouds are rolling away. So I'm not quite sure why. I think it was David's idea. Said, well, why don't we try from up here? Because we've got a couple of hours to kill before I had an appointment in the afternoon. And I got my portable kit in my handbag, hand case. So I said, all right. So we tried it from just on the roof of the car and didn't really get anywhere. And everything was floating around a bit. So again, I think it was David who suggested, well, look, that's that wall there where those people are walking. And the dustbin is. Why don't we just go and set it up on the wall? Okay. So there's that dish on a plate, an aluminium plate, so you could stick on it, gives it a bit of a footing. There is the transceiver, whatever you want to call it, the Pluto, the PA, an MRF driver, down a bias T. It's got something else in, can't think what else in the box, and a laptop. Couldn't be easier, could it, really? I mean, it's just silly. And we we just plonked it down. We didn't do any of the alignment stuff. We just plonked it down. And magically, the signals were there. So we never moved the dish again. We didn't dare move the dish again. We just carried on for about an hour. And there's an action shot of me. It was still chilly, as you can see. The waterproof jacket came in quite handy. But I was on my knees operating, trying to squint and see the laptop screen. You've all been there, I guess, trying to see what's on the screen in the bright sunshine. Now, that's a couple of other shots. Now, in theory, yeah, GW8TIX, GW8TIX. This is VO1 oblique G3V ZV portable. Thanks for the 5x9. You were 5x9. Signals are now dropping. There is slow QSB, but we proved. Thank you for proving that it does work. GW8TIX G3VZV portable VO1 oblique G3VZV portable Signal Hill, over. Thank you. 7 3s. VO1 oblique G3VZV portable Signal Hill, QRZ, over. What the locals thought of us as they were walking around doing their Saturday morning perambulation, I don't know. But there you go. So that was the end of our operation from Newfoundland. And I don't think anybody else has been back there since. I may be wrong. Not heard of any other operation. Anyway, quickly, lessons learnt and the thoughts for the future. We've said that the weather in mid-May can still be cold and damp. Gopan's mentioned, other people have mentioned, we noticed this QSB. Now, I don't think anybody has yet identified the cause for the QSB. Haven't really characterised it too carefully, too closely. Hasn't been monitored scientifically. My view is that it was about every 30 seconds and the signal would go up and down by about 30 dB. What that tells you, even if it's true, I don't know. I have a personal theory, not based on anything, but I wonder if it's signal rotation at the refraction point, and actually what we're seeing is vertical polarization becoming horizontal and backwards, and it's a polarization rotation that we're seeing, because it seemed to be sort of sine wave in level. I don't know. We could prove that after the event. It's very easy. We could have proven that while we were there, because we had 2 LMBs and we could have turned one around through 90 degrees and said, well, is it going up and down at the same level, or is it out of phase? So there's still lots of discovery to be found there, investigations to be done. I've talked already about, is it better to be higher up or lower down? And the answer is probably either or both, depends, and the 30-second fading. The other fading thing, of course, is the possibility that the satellite is doing a 3-dimensional figure of 8, and are we actually seeing it just at the top? Again, we don't know. And the final one is the occasional peaks, bursts of signal. Again, hard to explain, not often noticed, but when we were flying back, I did take a screenshot of flight radar at the time. That was sort of 2 o'clock in the morning, but make sure I push the right button. Yeah, I think Newfoundland is just about there, and you've got all these aircraft at 30,000, 40,000 feet. And obviously the spacecraft is over here somewhere. Is it possible that some of the signals we were hearing were aircraft reflection? Again, don't know. Yeah, 3-dimensional figure of 8. We didn't suffer, I don't think any of us suffered any equipment failure, which is really good. So we're quite proud of that. But we were careful to carry quite a lot of redundant backup equipment. I have to say, for the future, it'd be really, really good to have a beacon at Signal Hill, actually with a web SDR receiver as well, so you could really characterize what the path is like. The locals there were obviously concerned because it's difficult to get permission to put a big dish up, because it's a national monument, etc. Understand that, but even a small 35 centimetre, 40 centimetre dish hidden at the back of not at the back, but behind the parapet there. And of course the weather is diabolical and the winds are diabolical, so it would have to be very well built, but it would be a really tremendous asset to have. And again, I have to apologise for the lack of DATV. And the final sort of aside is you can never have too much gaffer tape on these sort of trips, or cable ties, or hats or gloves. So for the future, for the future. Should we go somewhere further? Sorry, we know that -1 will work. Thank you. Shall we go somewhere else for the future? Nearby, St. John's on this map is here. Nearby is a French département, Fox Papa something. Saint-Pierre and Miquelon. I can't pronounce the second word. But that's a nice off-lying island. Fairly easy to get to. You can fly to St. John and then drive down to the beach and get a ferry across. Shouldn't be terribly difficult. The weather, of course, is equally bad. So my final suggestion or offer or proposal or challenge is somewhere warmer, perhaps 8 Papa 6, Barbados. Does that sound more attractive? Yeah, okay. It's -4, which it's -4 degrees. 4 degrees below the horizon. So there you are. That's what we did. Hope I've 4 days in the 40 minutes or something. So thank you very much indeed. Happy to answer any questions. Either to Go Pan or myself. Yes. The question is, do we need a prize for the most Western QSO? Yeah, that sounds fun. Why not? So I'm just checking that AMSAT-UK will support that. Yeah, they will. Question there.
Just a question and a comment. Question was, did you point it direct? Did you use the Great Circle azimuth, or did you sort of go either side of it to find the satellite? And just secondly, just regarding the aircraft flutter, I think if it was bouncing off aircraft, you would hear some flutter, certainly on 2 gigs or whatever you're setting it up to.
Yeah.
As opposed to a change in polarization. I think that's I think just get the flutter from the aircraft more than anything.
Thank you. In terms of pointing angle, we used a. Oh, that's right. Yes, we used an Apple phone. So how does? Oh, yes, on a great. Yes, it was effectively a great circle. And in terms of the flutter and QSB and polarization, no, there were 2 separate effects. One was the very slow cyclical fading, and the other was just as a burst of signal. Now, I don't actually know aircraft reflection on microwaves. I hear it on 2 meters and 70 sems. Heard it on 23 sems. And it's sort of, well, it is flutter, isn't it? On 10 gigs, I'm not sure I've ever heard it, so I don't know what, well, I don't know. Okay, another question there. Hang on, let the microphone come as we have a microphone man. Thank you.
In terms of uplink power for phone comms, what was the sort of power ranges you were working to get successfully, into QO100? What sort of ranges were you at?
Yeah, I think when it was open, when it was working well, it was about the same as it would be operating here. So that very small dish, I had 10 watts probably at the dish, and that was more than enough. So that's the answer, really. Not a lot, nothing special.
Thank you. Just a quick question. Did the locals give any reason why they didn't use the beacon before? And a side question is the beacon still there, or is it been sent back?
Yeah, there was issues of people moving house and not having the equipment available. I think their main difficulty was to find somewhere to locate it on a permanent basis, and their I can't think of the name of the organisation that protects their environment. Say again? Parks Canada. Thank you, Ian. Parks Canada were not playing ball with anything. The ideal would be to find somewhere like Gopan operated from, a chap in a house or somebody who owns a house on the beach, and let somebody do what you were doing for an extended period of time. And I suspect they got this 1 metre dish, and so for them they had to use this 1 metre dish, and probably that led them down a path that made it more difficult than it need be. Okay, thank you. Oh, last question. Okay, that's a very, very timely question. I'm now going to say thank you very much indeed for listening to me again, and hand the microphone back to Dave.
Thank you, Graham. It's fantastic. Wish you have fun, and definitely technical challenges all around. Gopan, you received a certificate in my little bag here. Hold the microphone a second. Thank you. This is on behalf of AMSAT UK, and it's the AMSAT North America Challenge Cup, awarded to Ravi Gopan, the 01 M0XUU, for making the first two-way contact via QO100 on the 11th of May 2024. Congratulations. And ladies and gentlemen, we are now having a 15-minute break until, excuse me, 11:45, and David Berman, G0MRF, will be coming back to talk about FunCube Lite on the Jovian 1 satellite. Thank you very much indeed.
Okay, you want me to say something? Oh, perfect. With any luck. It was very nice to sit here watching Graham and Gopan doing their presentation on St. John's. I would say that I was there for 4 to 5 days, and it took me 30 days of antibiotics to get rid of all the things I brought home with me from St. John's. Okay, are we ready? Lovely. So this is one that you wouldn't have heard before. This is a project that's only been announced about a month ago. FunCube Lite is the latest project from AMSAT-UK. It's a fairly short duration project and it's running very, very quickly. If you are here because you think this is AMSAT-UK's first satellite to Jupiter, then sadly you are in the wrong place. This is definitely low Earth orbit, but there is some sort of logic to the naming of this satellite, which we'll go into. Okay, so we've got an opportunity to fly a payload on a 6U CubeSat from a group of universities. There is a collaboration between 4 universities in the south central part of the UK and a whole lot of industrial partners. The 4 universities in Space South Central are University of Surrey. We've got lots of good friends there and a history with that particular university, particularly the Space Centre. University of Portsmouth, University of Southampton, and another university who joined the group fairly recently, a University College in London. All have various departments doing space studies to varying degrees. Some are more focused on instrumentation rather than satellite missions, but all of them have decided to get together to try and promote space in terms of university studies and have, I think it's about 170 different industrial partners, primarily across Surrey, Hampshire, and the Isle of Wight. And when you look at those industries on a map, it really is very, very impressive, including people like SSTL, of course, who are a spin-off from University of Surrey some years ago, based in Guildford, Airbus, Kinetic, BAE Systems, and a whole host of other people that it was really good to see when I went through the listing. So Space South Central is essentially there to promote space studies and to liaise with industry to make sure the students are studying the right sort of things. 3 of those universities, Southampton, Portsmouth, and Surrey, have got together to try and do some work on real space hardware, which is something that's actually quite difficult to do in the UK. As far as I'm aware, there have only been 2 satellites registered to universities in the last 35 years or something. The original UOSat series from Surrey back in the 1980s, and more recently a satellite project from the University of Manchester. Other than that, all of the things being produced here are collaborations with other countries. So it's very exciting to see these people finally getting some designs ready for their students to put into space. So where does this Jovian 1 come from? Well, the program that's been designed by the 3 universities has been called Jupiter. And if you have a look at this, it's the Joint Universities Program for In-Orbit Training, Education and Research. So a very, very nice acronym. The idea, of course, is to be able to give students a bit more of a practical experience in putting things together for space. The liaison with industry will help the UK space sector's growing demand for specialist skills, so hopefully they'll have an input in some of the course content. And as I say, 170 industrial partners across South Central UK. This is hoped to be a rolling programme, and so if it's called the Jupiter programme, the first satellite in what will be a series is going to be called Jovian 1. So that's where the naming comes from. The press launch for this project was only the 20th of September, so what's that, about 3 weeks ago now. That's the press launch photo with students at Surrey University. And the first public glimpse of what this project is going to be about is this little representation of the satellite in the foreground there, a 6U CubeSat. And if you have a look at that, gravity is not working to the best effect there, is a deployable solar panel, 3 sections, a total of about 900 millimeters long. So this is going to have a reasonable amount of power, which is quite good. Also on the front of this 3D printed representation, a couple of patches. As far as I understand, this is going to be working on S and X band, but the satellite will use commercial frequencies for all of its science payloads. So looking at the satellite first, and then we'll have a look at the FunCube Lite payload in a few minutes. The satellite's a 6U satellite based on a structure and avionics from the Danish company GomSpace. It's going to be 3-axis stabilized, so it should be able to track a position on the Earth quite nicely. It's got a single deployable solar panel, which will give it a total power budget, if all the cells are sort of pointing in the right direction, of 45 watts, which is an amazing budget for a CubeSat, which is very good to see. On board the satellite, there are 5 payloads, 4 from the universities and 1 from AMSAT-UK, which we've called FunCube Lite. FunCube Lite, primarily because this is a very short timelined project, so we've had to basically get things that we've used before, either use them directly or adapt them so that we can get this produced as quickly as possible. The bands in use for the satellite will be S-band. It has an omnidirectional transmitter. Well, omnidirectional is perhaps a little bit overstated, because with a structure that's 6U high, an omnidirectional antenna is going to suffer some blockage, but nevertheless an omnidirectional is there before it manages to get attitude control sorted out. It will have a command uplink on S-band and a downlink on that frequency. But it also has an X-band transmitter on board. So X-band in this case is 8 to 8.4 gigahertz in terms of an allocation. And it should be able to get its Earth observation data down quite quickly and effectively if it gets licensed on that band. From an AMSAT perspective, the entire satellite uses a CAN bus for communication. I think there's LVDS in there as well, but we're not associated with that one. So any communication we do is going to be CAN based. It's not something we've done before very much. This is something that's going to be new for us, and he's certainly got a bit of head scratching to try and get around the various protocols that are in use within the CAN system. Very short project timeline. This whole thing started earlier in the year, around March or April. We've now got to a situation where all of that early preparatory work, which was essentially project planning and finance, has resulted in some orders being placed to GomSpace and other suppliers. Hardware is due to be delivered in the next couple of weeks, which is very, very good. And for us, we've got to try and deliver working payloads, so flight model payloads, by somewhere between December this year and February 25. So we've made some progress, but really it's a huge effort to try and get things prototyped, tested, and then a flight model being produced, and also some environmental testing before that as well to make sure it all stays in one piece. So here's a CAD image of what they're doing down at the University of Surrey at the moment. The project is based at the University of Surrey. Essentially a 6U satellite. So this is, in terms of size, 10 centimeters across here, 20 centimeters in this dimension. So if you like, 2 3U CubeSats side by side, and then 30 centimeters from top to bottom. At the top, this panel is in 3 sections. This solar panel just stows down this side, and when it's in space, that deploys, should all come out at 90 degrees. But the really nice thing about this is that at the central point on the solar panel, there's a mechanical connection, and that solar panel can rotate around one axis so that it has a degree of ability to follow the sun throughout the orbit. So if it works well, we should be able to get quite a decent amount of power from the system on the satellite. Just here on this face, this is the space-facing side of the satellite. The Earth is down in that direction, so Earth-facing is down there. There are patch antennas on the front of the satellite for S and X band. The S-band Omni is down here. I'm sure you can see that while it's Omni by name, there's an awful lot of structure behind that, but nevertheless, it should be quite useful. 38.4 kilobits a second is the maximum rate of the Omni. The X-band and S-band is much faster than that. In terms of AMSAT-UK, we're able to produce the circuit boards for the payload without any problem. But we needed antennas because with the existing antennas on the spacecraft, there was no UHF, no VHF antennas. So we've come up with a plan to fit an antenna deployer on the bottom. So if you imagine that facing the Earth, we've got a dipole with one element coming out of this side at the bottom of the spacecraft and the other one here. This element here is a 2-meter monopole. So what's that, about ½ a meter long, isn't it? So to give it some scale, we've got a satellite that's 30 centimeters and an antenna that's 50 centimeters long. So it's going to be quite interesting when it gets deployed. Hopefully that monopole will work okay, because with all of this other conductive metalwork down here, it should give us a reasonable earth for the monopole to function against. So previously we've used dipoles, they're automatically very efficient, but this time we've got to work a monopole effectively against Earth. So this is going to be quite interesting. Power system, 3-section rotatable solar panel, as I've said, 200 millimeters by 900. If the panel is not deployed, there's a total of 38 solar cells visible to space. Once the solar panel goes out, that increases to 70. So even if something doesn't go right with the solar panel deploying, there's still enough power to run the mission, but perhaps not with everything functioning 100% of the time. Energy storage on board, it's 85 watt hours, which is fairly decent, really, for a CubeSat. Lithium-ion battery based. Nominal voltage 28, although the reality is I think something like 26 volts discharged. 33.2 I think is the fully charged voltage of the battery pack. So we've also got to regulate that down to what we would normally find on one of our payloads, which is about 9 volts. So Jovian-1 payloads from the students. We've got some imaging payloads taking still and video images. Obviously, with the microwave downlinks, they can get video down, so that's going to be very interesting for Earth observation. So all 3 universities taking part in that. From Southampton, there's an intriguing dark matter detector. This is a technology demonstrator, sort of proof of concept. The dark matter detector actually has a laser system internally as part of the detection methodology. So although the laser is not exposed to space, we've still got to find the power to actually power that up. So it should be quite entertaining, and I'm sure it will be the subject of a few papers when the results of that finally come down to Earth and get written. Space radiation monitor, I think that's the physics department at University of Surrey. So they've got a radiation monitor that they've developed there that they want to demonstrate in space. University of Portsmouth have what I think we can probably think of as an AI payload, which is described as an innovative tiny machine learning payload. It essentially takes data from all of the other payloads on board and tries to analyze that, find patterns, predictions, and then sends those results down to the ground. And finally, FunCube Lite, which is really, I guess, our main interest. Ground station for the satellite is going to be based at Surrey. If you go past the universities, you can see a number of dishes on the roof there. This one is 3 meters. It's 35 dBi on S-band with a beam width of 1.6 degrees. So that's going to be fun on the first pass where you don't really know where the satellite is. So yeah, trying to locate the satellite with that dish is going to be a challenge. And if it's that narrow on S-band, you can only imagine how narrow that beam is going to be on 8 gigs. That's going to be extremely tricky to find. I think in reality, there'll be another dish or a helix or something mounted on the side to act as a guide. So if they can find that signal with a fairly wider beam width antenna, see that on a display, then they should be able to, focus in with the big dish. Uplink for commands is in commercial S-band, which is 2025 megahertz up to 2120. Downlink 2200 to 2290 megahertz is the allocation, so it will be somewhere in there, frequencies to be determined. And equally, the X-band downlink is 8 to 8.4 gigahertz, and again, there'll have to be some negotiation on available bandwidth and frequency allocation there. As recently as last weekend, this was all upgraded because you can imagine tracking something in deep space on X-band, which is what this was used for up until recently, is fairly easy. Things tend to move fairly slowly when they're orbiting Mars, for example. Trying to track S and X-band in LEO, however, requires something that can move quite rapidly. So in the last few weeks, they've upgraded the rotator system here, and they've got a new dish feed that's going to be fitted shortly with selectable right-hand and left-hand circular polarization for both bands. Just taking a look at that, not up on the dish yet. This is the dual band dish feed with the mount on the left-hand side, if I can find the laser. This is effectively an 8 gigahertz circular waveguide in the middle with the 2 gigahertz circular waveguide around the outside of that. Connectors on the bottom feed into the 8 gigahertz, and then you can just about see some holes drilled in the side of the waveguide there, ready for the probes to go on for the 2 gigs. So that's still being assembled. I think it's being manufactured in Holland, and that'll be mounted on the dish using these rods, 4 of those around the base of the structure. So it can be mounted up on the dish at Surrey for getting signals on those 2 bands. So having looked at the Jovian-1 satellite and their plans for it, let's have a look at the FunCube Lite payload. Well, most of this will be fairly well known to us because this is, I say, a very short duration project. Hardware delivery from us, December to February. And then I've seen charts that say environmental testing, vibration, thermal vacuum, fairly soon after that. And really with any of these projects that's being funded by a university, finding the funds for the satellite is one thing, but when you're employing a group of specialists, at some point that money is only budgeted to a particular date in the diary. So one of the things about this short-term project is that if you overrun it, you then don't have any money to pay the specialists. So the timeline here, I think, is going to be kept to within a very short margin. So FunCube Lite then, communications system payload providing BPSK telemetry, as we know and love from our various other missions. It will include, I think, 12 channels from our payload itself. but we'll also be picking up a lot of data from Jovian 1, including GPS data. So for the first time, we'll get data down via our telemetry to tell us whereabouts above the Earth the satellite is. And so that will be a first for us. We're incorporating a single channel FM voice transponder or repeater for amateur radio use. It will be UHF uplink, VHF downlink, and will have 67 Hertz CTCSS as standard. The BPSK telemetry and the FM downlink will both use the same frequency, which means that when we have the payload running, it will either be telemetry or it will be in sort of voice repeater mode. So we can't run both of those at the same time. Power saving modes, of course. CubeSats are infamous for being under budget in terms of power. So we've always incorporated lots of different ways of running our payload by being able to adjust the power, being able to adjust the amount of time it comes on. We can switch it on and off when it enters eclipse, for example, to save power. So there's lots of ways there that should guarantee that no matter what the power budget is on the main satellite, there's still enough power to run our payload, which is good. Manual mode change can be done via a UHF uplink, so we have to be able to command it legally anyway to be able to turn it on and off. But as I say, it can change modes on eclipse entry and exit if we need to. We're using flight-proven hardware where we can, either directly by taking a design that we've already got and using that, or by taking small modifications to existing hardware in some cases. So we're taking elements of hardware used on UCube-1, JY1-SAT, and the ASAO missions. And also, of course, we've got the Windows-based ground station software, which will decode all the telemetry as it comes down, and an online data warehouse to store all the data, which was particularly interesting to University of Surrey because, of course, they can have students in future years do analysis on data that we've collected. So that should be good for everybody, I think. So moving on the right-hand side is one of our earlier projects, but the purpose of it here is just to show the construction. We are using a 4-board solution based on PC104 CubeSat format, so stacked with supporting rods. So we have a standard size printed circuit board with 4 rods in the corner, all held together with spacers and headers that interlock. So that isn't the format being used for the student payloads. The student payloads are using a more conventional for space tray assembly. So all of their modules will be built into trays that can be plugged in and out. But because of the time pressures, we're going for this format. The stack height will ultimately be about half a U or thereabouts. So about half the size of a 1U CubeSat, but mounted inside. And if we have a look through there at the 4 boards, we've got a VHF-UHF communications board. 435090, I think, is the frequency we're going to apply for. We have a VHF power amplifier with an FM transmitter mounted on it this time. So the amplifier has flown before, but we've added FM transmit capability. Command, control, and telemetry, which is something that we've used on previous missions and is fairly well proven with a lot of flight heritage. And finally, something which we've called Cannibal. I think the author of that name standing at the back somewhere. Cannibal is the CAN interface board for AMSAT Lite. Well, you've got to have some fun somewhere, haven't you? That board will carry a CAN interface to the rest of the satellite. Because we had space on that board, we've decided to pop a radiation sensor of our own on it, and the switch mode power supply that's necessary to take the 28 volts down to 9 volts for our mission. We also need, though, the antenna deployment system, and no one in AMSAT-UK has the experience to put one of those together. And the reason is these things are really mechanically based. So we've turned to some old friends, Isospace in the Netherlands. One of their best-selling products is their antenna deployment systems for CubeSats. On the right-hand side, we've got an example of that we've flown on all of our missions that have been CubeSat-based. You can see it deploys 4 elements in standard format. So on this one here, you might have a 70 SEMS dipole across these 2 elements. And then vertically here, in previous missions, we've had 2-meter dipoles fitted like this. Internally, this is a CAD image, which is available on their website. It is a true mechanical work of genius. I mean, for this thing to be so reliable, it is amazing. And internally, we stood no chance of producing something anywhere near the reliability of this product in the short timeline. So we've just taken a dip into members' funds and we've splashed out some money. And this is on a bit of a lead time, but nevertheless, it's been ordered for this mission. So the FunCube Lite satellite, if you like, block diagram or system connection diagram looks something like this. Top left-hand side, we've got that Isospace antenna deployment system with its UHF and VHF antenna. Immediately beneath that, we've got the transponder board, which is essentially a UHF receiver, the telemetry generation, and the repeater logic and timers. To the right of that, we've got the CCT board, which does all of the command, control, and telemetry. We'll have a look at each of these in a minute. The RF power amplifier is above. That's something like 29 dB gain and about 600 milliwatts out. And then on the right-hand side, we've got the Cannibal CAN interface board, and importantly, a harness connector to the rest of the satellite with power supply lines coming in, CAN coming into it, and a loop through with CAN coming out. So quickly through these pictures I think have been used before. This is the command, control, and telemetry board. It's based around 2 pieces of semiconductor. First of all, a Xilinx CPLD, which acts as a command decoder, and also it formats the modulation for the telemetry. This is a particularly reliable system because the other piece is a microcontroller from Freescale. Microcontrollers have been known to fail in space before, but this Xilinx firmware, if you like, has been ultimately reliable. And even if the microprocessor fails, it still means that we can control the mode selections on the satellite. So we can have complete microprocessor failure. We've still got direct access to being able to switch modes by using this type of topology. If you've got any questions on any of this, Duncan is standing at the back, and I'm sure he can answer questions later if you want. The first version of this was launched in 2013 on AO73. It's still working 11 years later through some pretty amazing solar activity at the moment at 600 kilometers and hasn't failed. A little bit of an internal diagram here. I'll try and speed up a little. The internal diagram of the CCT board is there with the Xilinx CPLD at the top and the processor underneath. Only an 8-bit processor, but we are very, very mean with power on this. So if we can do it in a simple format with minimal power, then that's what we choose to do. The telemetry coming down, this is, I think, from AO73. It's a mixture of whole orbit, real time. I think we've had high resolution data on this one, which is once a second. And we've previously used fitter messages, so little text messages for school outreach, where we can upload a text message and schools can download that and their students can go, hey, that's my name coming down from space. That's pretty amazing. I think we had 9 or so for AO73. We'll probably cut that back a little now because we've got other data from the satellite that we would want to include. PA board, loosely based on our previous missions, upgraded to include a driver. Also, we've included a combiner on the input. So with this board, we can have input signals from various sources on board a satellite and just combine them and then amplify them and transmit it out. It's a Mitsubishi amplifier, an FET. It's got 4 channels of telemetry on board, and basically I think we worked out this has spent 25 years in space, this particular PA design, without a failure on several different missions, obviously. On the bottom side of that, we've just adapted it. This is the entire FM circuit here. That's an entire FM transmitter. We sort of thought we'd go for the easy solution here, the minimal component count. The FM transmitter is just one chip. Silicon Labs SI550, which is a voltage-controlled crystal oscillator. So the idea is we should be able to apply a control voltage to it, and it frequency modulates it. That seems to work very nicely. The other components here are just basically a low-pass filter to get rid of some of that high-frequency hiss that would otherwise cause the bandwidth to be quite wide. Does it work? Yep, we've done a linearity check on the engineering model. Nice and linear up to 500 milliwatts. We've pushed that a little bit since then, so it goes to over 600. For VHF, that's perfectly okay. FM transmitter testing, we need to test this stuff on the ground first. We needed to set the deviation. We chose 3 kilohertz as a reasonable figure. Deviation meters aren't terribly reliable, and I don't have one anyway, so we had to find another way of doing it. We found a method used to assess deviation by nulling the carrier. So when you transmit a carrier, you get a single frequency. If you apply FM and you turn the volume up with an audio tone going in, you can calculate an audio frequency where you turn up the deviation, the power of the carrier just disappears down or is a null. And that's an extremely accurate method of measuring deviation. So we went for this technique. Funky light telemetry, I think we've looked at this on many other occasions. So 1200 bits per second BPSK, 24 5-second frames to get all the telemetry down over a 2-minute period, real-time whole orbit and text messages. We've also got a little bit of expanded memory capacity on this, and as there is an imaging payload on board, we've yet to talk to the students doing that, but they've expressed interest in that, well, if their payload doesn't work entirely as planned, we might be able to grab small resolution, low resolution images and transmit that down as part of the telemetry on board FunCube Lite. VHF comms, as I say, UHF receiver in the middle, providing command audio, and up at the top here, we'll route the audio in this direction for the transponder function. 8 channels of telemetry available from a Maxim chip, which gives us 12 overall. And the baseband telemetry is also modulated on this board, and it gives a low-level output going to the PA. So that's essentially how it operates. Loosely based on these 2 boards, half of the board at the top, which comes from the ISAO mission, and about a third of the board from the bottom. So it's a bit of a mishmash there. We certainly can't use these boards as they are, but we can take elements that we know work, combine those, and with a bit of luck, that should be what we're flying on ISAO in a much modified form. Cannibal, the CAN interface. Again, Duncan's in charge of this one, so any questions on CAN, or perhaps we can ask you some questions because we're still very much learning. A PIC processor with a CAN interface on it, CAN transceiver to interface to the satellite bus, We've added a BG51 radiation sensor, which is an array of pin diodes to detect beta, gamma, and X-ray. The radiation detector is this one at the top. It's just a 3-terminal device. It takes 25 microamps, I believe, at 5 volts. So almost any CubeSat can fly one of these without any effect on the power budget. We've tested it at a local school with some gamma and beta sources. Appears to work very well. So that should be incorporated as well. Okay, so coming towards the end now, and there's a lot of questions that have remained unanswered so far. Jovian 1, we know it's under construction, we know it's financed. When is the launch date? Who's the launch provider? Whose rocket are we going to bolt this thing to? Where's the launch site? Will we be able to go and drive and see it, for example? What's the altitude in orbit to give us an idea of where this thing is going to enable us to communicate? The inclination of the orbit, we'll be able to hear it up in Scandinavia. The lifetime of the satellite, think of that huge solar panel hanging out. That's going to have a lot of drag. That's going to be an interesting one. And of course, the concept of operations, how much time will the payload actually be on? Sorry. Yeah, all of this stuff, to be fair, we don't know much about it anyway, but we can't say because there's a non-disclosure agreement in place. What I would say, though, is this project is very fast moving. And if they're going to meet the budget, then all of these things have to be sorted out fairly quickly. So I think we can anticipate there are going to be announcements on all of these topics in the short term rather than medium or long term. So we'll just have to look out for those when they actually happen. Which leaves us 5 minutes for any questions, as long as it's none of these. I think there's a microphone around somewhere.
Thank you, I've got one.
Oh, well done.
The age-old question, CTCSS, why have we incorporated that? Because obviously you want to use some digital modes, which we've done before on D-Star search. It's a bit of an inhibitor.
It is, but bearing in mind this is an FM receiver and an FM transmitter, you have to sort of limit it somewhere, and you can't run it completely open because of the effect on the power budget. It's just what we felt we could do in a short period of time without perhaps realizing the potential of other types of modes. So if you'd like to have a chat with us about other types of modes, there's plenty of bar time and coffee time left. I'd be very pleased to talk to you about that.
Dinner.
Dinner, okay, well done, got your ticket. Any other questions? Okay, got another 2 here. Is there a microphone just behind you, Dave?
Thanks very much. Yeah, hi, thanks. Yeah. Probably a very basic question, which everybody else knows the answer to. Apologise. You were saying this, the satellite has got an Earth-facing side,
yes,
and a space-facing side. How do you maintain that orientation? Because I was thinking drag on the solar panels might well cause it to rotate.
Yeah, indeed. The traditional way of doing that, of course, well, the need for that is if you've got a camera on board, you want the camera to point into the right place. So you must have the ability to point the camera at the object you want to photograph. Equally, if you've got microwave patch antennas, they have a fairly wide beam width, but again, you've got to make sure it's Earth pointing to get that antenna pointing in the right direction. The answer is, you're in low Earth orbit, so there's a magnetic field. So if you have something called magnetorquer rods, you can pulse current through them, and they exert a force on the satellite. So they move the satellite by magnetic interaction with the Earth's magnetic field. There's also, what do they call the wheels? Momentum wheels? Reaction wheels, and that gives it a much more smooth slew. So if you're taking a photograph in one position, as the satellite's traveling at 7.6 kilometers a second in orbit, you perhaps need the camera pointing at an object over several seconds to get the image you want. So there are a couple of different methods of attitude control on the satellite. But you're right, that solar panel's enormous, isn't it? Any other questions? I saw one over here.
Yeah, so the question was pretty much about the same, yeah, about stabilization. So, but all the ways you mentioned, they're quite power hungry, let's say. Yeah, and because you need to rotate the satellite quite often, yeah, because it's a low orbit one. So the question is, was it used on the previous flights or not? I mean, such kind of idea.
Yeah, I mean, this is a standard method on most satellites. Actually,
yeah,
most
but for small satellites, was it used
yeah,
before?
in fact, on one of our missions, JY1SAT, which is obviously owned by Jordan, but nevertheless has a FunCube payload on board, there's a small board on there which has smaller versions of torque rods and coils on board, and that has the function of stabilizing the satellite, because sometimes when they're ejected from pods on the host rocket, they can come out tumbling, and the important thing there for communications is to get the things stable so that they're not rotating out of control. So yes, it has been tried, and if you get the software right, it works really well.
Okay, thank you.
Okay.
Hello, you mentioned a protocol to get telemetry. What about images? So will they be publicly available?
I think the students will want to see, and certainly remember that one of the objectives of this whole project is to make potential students aware of space studies. So if you want to attract students into your university, I can't imagine why you would take a photograph and not publish it. So I would think there's going to be a lot of these photographs published coming down on S and X band. If we get to send anything down, it will be lower resolution because our data rate is very slow in comparison with those other bands. But if we can do that, it will be an interesting thing to do. We have sent down still images before on JY1SAT, some lovely pictures that were preloaded. So we know we can do it at this data rate. It's just a question of who formats the image, which might be several megabytes, into something smaller and then transfers it to us. So yeah, in discussion.
Thank you.
Okay.
And actually, while we're talking of software, do you have any facilities for changing firmware in flight, or is it all baked in on the ground?
I would have to say baked in on the ground, as I look to my software developing colleague at the back, who's shaking his head. He's the one to talk to later if you've got plenty of software questions. But no, we program this on the ground. And then after that, it's just a question of executing whatever we've managed to program in it. Hopefully, we think of all the scenarios. Sometimes we don't, but we're left with whatever there is on the satellite. But hopefully, by the time we're here next year, this will have progressed a very long way from today's brief chat. Thank you, Dave.
Thank you, David. And I'd like to thank him, please. I'd like to say something as well about FunCube Lite. Dave keeps saying we. The we is the FunCube team, and to whom we are very, very grateful. FunCube 1 has been 11 years old, and that's a measure of how good the design was, and the same thing is going to go into this as well. My other comment is, David also mentioned that we'd be talking about collecting data in the data warehouse. When we started out, we had about 2,000 people collecting that data. As things have changed, that's dropped, of course. So this is another opportunity for people out there to actually feed us more data into the warehouse. And from my point of view now, it's a break for lunchtime. We resume here at 1:45. Thank you very much indeed.
Well, hello everybody. Welcome back for the afternoon session. We have a guest speaker on Zoom, Craig Underwood, who is from Surrey University, and he's going to talk about space-based power. So, Craig, if you want to go ahead and share your slides, and the floor is all yours.
Thank you very much, Ian, and good afternoon, everyone. So welcome to this talk. So let me just share my screen. And away. And hide that.
Yep, that looks fine, Craig.
Great. Okay. So good afternoon, everyone. Welcome to this presentation. As Ian said, I'm Craig Underwood. I'm Emeritus Professor, actually, at the University of Surrey. And it's my pleasure to present some of our work on solar cell technology and space-based solar power. So just a little bit of my background. I've been here at Surrey now for coming up to 40 years. I first came involved with the UOSat satellites, good old Oscar 9 and Oscar 11, when I was a school teacher back in Scarborough in the early 1980s, and setting up a ground station there and using that with my students. Through that, I got involved in satellites in education and working in the ground station, as you can see in the picture there, at Surrey. And then because of my physics background, I got involved in the actual design of the spacecraft. So I used to do all the thermal design and all the radiation protection of the SSTL, Surrey spacecraft. My research was mainly about sensors, looking first of all at radiation and then optical and radar type sensors, and also looking at the systems of spacecraft, including, of course, the power system. So I formally retired in 2019, but anyone who's ever tried to retire will find they're busier than ever. So life goes on. At the Surrey Space Centre, which is the academic side of the University of Surrey, it's different to the company, spin-out company SSTL. We've done a number of missions in recent years, all based around CubeSats. In fact, all based currently around 3 CubeSats, starting with Strand 1 in 2013. And our last mission was actually a big satellite, which SSTL built for us, and that was Remove Debris, which some of you will have heard about, I'm sure. But today I want to focus on a mission we did in 2016, which is called ALSAT-1 Nano. And this was a satellite built as part of a know-how technology transfer program with Algeria, and it was paid for by the UK Space Agency. And as sort of quid pro quo for that, it flew 3 British payloads. The payload I'm going to talk about is the solar cell payload, but first of all, a little bit about solar cells, or what we scientists tend to call photovoltaic cells. Of course, they've had a long history in space. In fact, when silicon solar cells were first produced in the sort of 1950s, they were so expensive that really only a space program could have possibly afford them. And so, of course, they saw very early use in spacecraft. And so through the 1960s into the 1970s, and actually, in some cases, even today, silicon junction solar cells are still used. But in the 1980s, we had the so-called 3-5 semiconductor, compound semiconductor solar cells based on indium phosphide and more commonly gallium arsenide. And then multiple junction cells started to appear, first dual junction cells, and today triple, and actually even quadruple junction cells. And throughout that time, the efficiency of solar cells has got greater and greater and greater. When we started with the UOSats, we flew silicon cells at 12% efficiency, and today typically we will fly triple junction cells at about 28% efficiency. And that's been achieved through using a sort of sandwich technique where the different semiconductor junctions are picking off different parts of the spectrum of light. And so we can use more of the sun's light to generate electricity photovoltaically. Well, while that's all been going on for space, in the terrestrial world, there's also been a revolution in solar cell technology, driven by the net zero race and the urge to go green. And one of those developments has been the development of what we call thin film solar cells. Now, in these kinds of cells, we use quite complicated chemistry to make a very thin layer which can be laid down on a substrate, and that substrate could be a plastic film or it could be extremely thin glass, so thin that it's actually flexible. And this makes it a very cheap process because it can be printed almost like printing on a piece of paper. And so the cost per watt is very much reduced. So the Centre for Solar Energy Research, now at Swansea University in Wales, and ourselves here at Surrey, we got together to work on adapting this technology for use in space. And the idea was to see if we could make a technology available for use in space that was far cheaper in terms of dollars per watt or pounds per watt than hitherto was possible. So we were sponsored by the EPSRC, by the Engineering and Physical Sciences Research Council, and we worked with industry. We worked with a glass company called Keyoptic, who make the cover glass for solar cells in space, and we use their glass as a substrate for printing our solar cells on. And we also worked with SSTL as a potential customer for this technology. So the key innovation from the group at CSER in Swansea was that they had the facilities to lay down what's called metal organic Kappa vapor deposition. So essentially, you can put a substrate in a reactor and then expose that to a gas, and the gas lays out on that substrate over time, and layer by layer you can build up the multiple layers that form the semiconductor material. And the material they were using is cadmium telluride. And in fact, to make it work, you need several different kinds of compounds. So we start with sort of conductive layer. We have cadmium sulfide, cadmium zinc sulfide, cadmium telluride. So this very complicated chemical sandwich is gradually built up, and it forms a junction, which can then act as a photovoltaic source. Well, the glass that we used was incredibly thin. We asked Keyoptic to give us essentially the thinnest glass that they could easily make, and that turned out to be about 100 microns. So what's that? About 1/10 of the thickness of a human hair, something of that order. And it's so thin that it really is like paper. It can be bent very over a great radius. So it's a very flexible material. So the advantage of this technology is it's low cost. It provides a potentially very large area solar cells, because you can print over a large area depending on the size of the reactor. But the key parameter for us is cost per watt, but also what we call specific power. That is, how many watts of power do you get for every kilogram of solar cell you fly? And I'm sure many of you know that every kilogram we put into space costs us an absolute fortune. Typical cost for a kilogram to orbit is of the order of $20,000 to $30,000 normally. So for space engineers, weight is everything, and we try to get the lightest weight possible solutions to all our engineering problems. And the cost is good too. So the final costs of this technology is something like 1/5 of the cost per watt that we would get associated with traditional solar cells. But the specific power of these solar cells is fantastic. So the cells that we were manufacturing had a specific power of 0.65 kilowatts per kilogram, which is an enormous figure. Compare that with the best efficiency triple junction solar cells, it's nearly double the specific power that's available from them, even though the efficiency of triple junction solar cells is much, much higher than the efficiency of the cadmium telluride cells that we were working with. So 36% for the very best for triple junction cells against 14% that we had then. Although it has to be said that now we're closer to 20-25% for the cadmium telluride technology. Now, solar cells, like all parts of a spacecraft, see a very hostile environment as we launch into space. The act of launching itself is is the roughest possible ride. You have phenomenal vibration, phenomenal forces acting as you accelerate into space at tremendous rate, but also you get the shock from the staging of the rocket, and that's done explosively, and typically the shock that's carried through the structure of the rocket into your satellite, and therefore into your solar panels, is of the order of 1000 G. So it's a bit like taking your mobile phone, holding it at shoulder height and just dropping it onto concrete, which I don't recommend that you do. So obviously we needed to make sure that our solar cell technology was very tough to be able to withstand that, and to be able to withstand the extreme thermal cycling that we see in space, and also the extreme vacuum conditions. So in sunlight, of course, we get the full blast of the sun's rays. There's literally nothing between us and the sun. And at Earth's distance from the sun, that's at nearly 1.4 kilowatts per meter squared of heat flux, essentially, coming into the solar panel. But when we're pointing away from the sun, pointing at deep space, all we see is about 4 Kelvin, so about minus 270 degrees Celsius space. And so the outside of a spacecraft is subject to extreme cycling. In fact, I've put a little plot at the bottom there, which is real flight data from good old USAT-2, Oscar 11. And you can see that in our sun-synchronous orbit, about just about 100 minutes, you're getting down to about minus 35 and up to about 12 degrees C, just going around the Earth. So one thing that we did is what's called a pull test. You literally use sellotape, Scotch tape. It's an industry standard test across the world. You put the sticky tape over the cell and then you pull it off. And what you hope doesn't happen is that any of the solar cell comes off with the tape. So that's a pull test. We also did thermal shock testing, and we also did mechanical vibration tests as well. Now, the thermal shock is extreme. You heat it up to 80 degrees Celsius, so nearly getting on towards the boiling point of water for 1 minute, and then you plunge it into liquid nitrogen. So liquid nitrogen is minus 196 degrees Celsius. So the shock from going instantly from 80 degrees Celsius to minus 196 Celsius is extremely violent. And again, we hold it for a minute, we pull it out, heat it back to 80, and we keep doing that 20 times. And if it survives that, then it survived the test. So as you can see, the testing is extreme, but we have to do that to get materials that can survive the space environment. Sorry, we have very good facilities for looking at the microstructure, almost, well, actually down to the atomic level. And here you can see some photomicrographs of the structure of the different layers inside the cell. This was done by X-ray techniques and electron techniques. If you look, it's very sort of lumpy and bumpy. In fact, it's very disordered compared to a monocrystalline solar cell. This is definitely not monocrystalline. Every little bump you can see is essentially a separate crystal. And really, it can be described, I would say, as being chaotic in nature. And that has led to an interesting property that we discovered, which is that it's very robust to ionizing radiation. Normally, when we expose a monocrystalline solar cell, standard space cell, to the ionizing radiation in space, it degrades quite rapidly, actually. And the mechanism through which it's degrading is that the incoming cosmic rays and protons and even electrons cause the atoms of those crystals to be knocked out of their proper location. So they're displaced. And that leads to a quantum mechanical effect, which can trap charge. And that slow charging up of the structures leads to their performance degrading. But I think the reason our solar cells made from cadmium telluride are so robust against radiation is that they're already chaotic, and so they don't get any worse when exposed to ionizing radiation. One good thing about cadmium telluride is that the band gap energy of the semiconductor is quite high, and what that means is it responds pretty well across a broad area of the spectrum, all the way from near ultraviolet to near infrared. So it maps very well, and that's why it's a good material for this purpose. So I talked about the radiation environment. This is a little graphic that shows that. Of course, we are bombarded by trapped radiation, the Van Allen belts that were one of the first discoveries of the space program. If we're in low Earth orbit, we keep dipping into the inner Van Allen belt over the South Atlantic anomaly, and we dip into the outer belt actually as we go over the poles. So if we're in a sun-synchronous orbit, which is a near polar orbit, we get the worst of all worlds as far as low Earth orbit is concerned. If we're higher up, further out into space, say geostationary orbit, then we're in the outer radiation belt, and we get zapped all the time by high energy electrons. And when the sun is particularly stormy, as it is right now, some of you might have seen the aurora the other night, it really populates the radiation belts temporarily, and we get absolutely fried by radiation. So it's something that all of us have to be aware of in designing electronic systems for space. So here you can see the effect of radiation on what we call the current voltage curve of a solar cell. So this characteristic curve is the pattern that you get from a solar cell. This point here is called the open circuit voltage. That is, if you just put a multimeter in volt mode over a solar cell that's illuminating, you'll get a certain voltage, but there's no current flowing because the multimeter has essentially an infinite impedance. So it's just a voltage, and you get VOC, open circuit voltage. The other test you can do is put the multimeter into current mode, which is a dead short circuit, and get the short circuit current. Now, if you think about it, if you've got current and no voltage, or voltage and no current, in neither case do you get any power, because power is the product of current and voltage. So it's only at the knee of this curve, when you have a voltage that isn't quite as high as the open circuit voltage and a current that's not quite as high as the short circuit current, that you get power. And the way you achieve that is you connect the cell to an impedance that happens to hold it at that knee position. So a key thing about solar cells is that to get them to work efficiently, they have to be matched to a particular impedance. And unfortunately, that impedance changes all the time. And so our best power systems have dynamic impedance matching, and they actually track the maximum power point of the solar cell. So here you can see how gallium arsenide and silicon degrades with radiation exposure, and it's all to do with this displacement that's going on. Now, to actually test this, we put it in a radiation beam here. Sorry, we have a particle beam, and we hit it with protons. So actually quite low energy protons, but we deliberately chose an energy of proton that would cause the maximum possible damage inside the solar cell. This is a simulation of that, but we actually did this for real. And what we found is that the cells were about 100 times more resilient to radiation than conventional solar cells. So to put that into context for you, if we are designing a space mission these days, say in geostationary orbit, to last maybe 20 years, these cells would last 2,000 years. So that's very encouraging and good news for us. So obviously we wanted to get some actual flight experience, and just by fortuitous chance, at the same time we were working on that, Surrey and Swansea, we were simultaneously training Algerian engineers with the AMSAT-1N mission, a little CubeSat mission, and that would carry 3 UK payloads. So Swansea put in a bid to fly one of their solar cells. Oxford Space Systems put in a bid for their boom, and the Open University put in a bid for the camera, and they were the 3 winners. And so we got to work on putting together a flight payload, which we call the Thin Film Solar Cell Experiment payload. So at Swansea, they manufactured a set of test cells for us, and although it looks like one sort of little black patch, there are 4 1 centimeter squared cells in that patch, and they had to lay down all the gold contacts so that we could get electricity out of the cell, etc. And I did the electronics because I got experience of doing this sort of thing in previous missions, in fact, going back to USAT 4 and USAT 5. And so using a microprocessor controlled system, microcontroller controlled system, I was able to put together a circuit to measure the IV curves actually in space and to measure the temperature, and to do that with extreme precision, so 12-bit precision. And so we get very good, if it worked, we get very good flight data on their performance in space. So there's the little board. And of course, being a CubeSat, all this had to be squeezed into a PC-104 board, which is roughly 10 by 10 centimeters. Well, this is the IV curve that I was just discussing, and there's the maximum power point. You can see that at that point we get the biggest area of that rectangle, which is the biggest power. So with the 4 test cells, we used solid state switches to switch each one in turn. And then I made up some instrumentation amplifiers to measure very precisely the voltage and current and connected it to a programmable current sink. So in other words, the circuit demands a current, the solar cell tries to give that current, and then we measure the voltage and the current simultaneously to check its performance. And before flight, we tested them at Swansea using proper solar simulating light sources. We can use what's called AMS 1.5 lights, which represent the sunlight levels on average on Earth, and AM0 lights, which match the sunlight intensity in space. And of course, the AM0 lights have a lot of ultraviolet light in them as well, because of course it's not absorbed by any atmosphere. So we measured the efficiencies, etc., and here's the IV curve actually measured for those cells. And then that was delivered to me at the Space Center here, and I put that together. This is the one of the solar panels on the CubeSat and the test cells there. I used a standard torch, quite powerful one, to test it just for functional testing. And then when it was all wrapped up and ready to fly, we took it out to India and launched it on a PSLV launch vehicle. And so on September 26, 2016, it was launched into a sun-synchronous orbit, so about 700 kilometers altitude. And in fact, all the payloads worked. So Oxford Space Systems worked. There is the boom deployed as imaged by Open University's camera. But certainly the solar cells worked. And this is the first flight data. So if you see, there are 4 curves there. They're very close together, which is a good thing. It means all 4 cells are working and tracking together. And there's the open circuit voltage at about 0.95 volts. And there's the short circuit current at about 25 milliamps for a 1 centimeter squared area. Well, over the years, we've seen it change. We've seen it degrade. And that's been very interesting to watch. And the other thing is that AMSAT-1 was designed for 1 year lifetime because the batteries on CubeSats tend not to last very long. We designed it for 1 year. We kind of hoped we might get maybe 1.5, 2 years, 3 years perhaps out of it. But actually we got more than 6 years. In fact, in the end, I think we got over 7 years of design life out of it. And the payload carried on working. So we got way more data than we expected. In total, over that 6-year period, we got 150 surveys, 30,000 orbits worth. And as you can see, year by year, the curve goes down. So the open circuit voltage drops and the short circuit current drops as well. And the curve also gets flatter and flatter. None of this is good, by the way. It means the efficiency is dropping down. So we wanted to know why. What was it about being in space that was causing that degradation? Well, first of all, I asked the question, is it my circuit? So my circuit had built-in auto-calibration by measuring resistances, etc. And you can see it's perfectly linear and remained perfectly calibrated. So it wasn't a measurement fault. The measurements were accurate. So what could it be? Could it be temperature? So we measured the temperature with temperature sensors under the cells. And there in the blue dots are the degradation in efficiency, and in the red dots are the temperatures when we measured those degradations, and you can see that the red dots are scattered. So in other words, there's no correlation with temperature. It's not a temperature effect. In fact, the temperature effect shows up very nicely as an expected slight linear drop. Solar cells, when they're hot, are not quite as efficient as when they're cold, and so that's to be perfectly expected. We also checked if the fill factor, that's basically how rectangular the shape looks, varied with temperature, and it certainly didn't. So the conclusion was it's not temperature. So what else could it be? Well, if you look at a model of a solar cell, it's modeled as a current source, a photocurrent source, a diode, because it is a PN junction after all, and it's got impedance. It's got a a shunt impedance, a parallel impedance, and it's got a series impedance as well. So you could model that as two resistors. So this is not an electric circuit. This is an electrical model of what a solar cell is like. So if these impedances change, the behavior of the cell will change. And in fact, what we can do is we can look at the change in behavior and find out how these impedances are changing. And what we discovered is that the series resistance isn't really affected much at all, which is a good thing. But what we did find is the shunt resistance was dropping. And that's a bad thing. If it gets less and less impedance across the cell, it means that there's a bypass of the current and we don't get that power coming out of the cell. And in fact, it was exponential pretty much in time. And that was interesting to observe, very clear signature. And it wasn't to do with the space environment. What it was to do with is the fact that to do the experiment and get it ready for flight in just a month or two, we had to make some compromises. And one of the compromises we had is we couldn't change the electrical contacts at the back of the cell from gold. We had gold contacts, and we knew that in the space environment, that gold could become mobile. So atoms of gold could leave the electrical contact and migrate into the cell. And that as they did so, that would form a conductive path through the cell and effectively short out the shunt impedance. And that's pretty much what we saw. So it fitted very well with other observations from other tests that had been done on cells over the years. And indeed, we kind of knew that that might be a possibility before flight. So in the future, we would have different systems on board. So what are the next steps? Well, we'd like to fly it all again. Next time, flight with a proper back contact. We'd have to make a different kind of metal back contact. And also, we'd like to try what are called concentrated cells. The picture on the right there shows a Fresnel lens over a solar cell. It turns out solar cell material is quite expensive and lens material is quite cheap. So it actually is cost effective, although a bit heavier, to actually have a lens focusing the sunlight onto a smaller area of solar cell. Of course, you get a much greater light flux on that area, and you can actually get way more power out of the cell that way. But there are all sorts of issues. You've got to have the optical alignment has to be right and so on. But we want to try that in space. And so I've come up with another version of the thin film solar cell experiment called ASCOT that I hope to fly in a couple of years' time. And what I would like to do is fly Swansea's cadmium telluride cells again, but also fly cells developed by my colleagues here at Surrey, Jay, who's producing a material called perovskite. Perovskite is a sort of copper compound, and it looks very promising, but it's not really had much flight heritage in space yet, and there are some issues with it that we think we might be able to solve. And also, I'm in contact with the University of Cambridge, with Louise's group there, and she's working on thin film gallium arsenide cells. So the ideal for me would be to fly all these technologies together and get comparative data on their performance. And also, we'd like eventually to unroll these solar panels in space. So instead of having deployable solar panels that are rigid, we just simply unroll them. So why are we interested in thin film solar cells from a space point of view? Cheaper, better specific power, but that leads us to be able to have much, much bigger solar arrays so that we can generate much more power. And there are so many applications in space that need huge amounts of power. I mean, communication satellites these days typically have powers in the tens of kilowatts. So they already have big but rigid solar panels. The space station has got about as much electricity as a sort of hospital or something like that. It has very big but deployed solar panels. Actually, they're not rigid on that one. Moon bases, bases on Mars. But the one that I want to talk about is space-based solar power. So it sounds a bit science fiction, doesn't it? And in fact, it started in science fiction with Isaac Asimov in 1941, writing one of his short stories about robots. And his robots were tending a space-based solar power station. So a power station in orbit using sunlight to generate electricity and then beaming that electricity down to the planets. He doesn't say explicitly, but we might assume it was using microwave power. Now, this was taken quite seriously by NASA, and so a gentleman called Peter Glaser in the 1970s studied it very carefully for NASA and found it was quite feasible. We had the technology even then in the 1970s to generate solar power in space and to convert that pretty effectively into microwave energy, beam that microwave energy to somewhere else, and then rectify that microwave energy back to AC electricity again, or actually DC electricity, and use that to do something. In fact, an experiment was done with the Goldstone antenna, one of the Deep Space Network antennas, where they did exactly that. They connected solar power to it. They powered the microwave transmitter on the antenna, and they beamed power to a mountain, I think a few miles away, and then they converted that to light up some car headlight bulbs. Today, we can do this way more effectively because we have gallium nitride and other very high efficiency semiconductor-based amplifiers. And so we have a very good conversion efficiency from light to electricity in the solar cell and from electricity to microwave in the amplifiers, and then out from microwave energy back to DC electricity in what's called a rectenna, a rectifying amplifier. So the technology is there, but it was never practical because it would just cost too much. And certainly in the 70s, we couldn't really build the infrastructure in space. And even in the 80s with shuttle, we couldn't do it really practically. So it's been looked at decade after decade. But the drive now is the green agenda. Is it worth looking at it again to see has something changed? And what's changed is something no one expected. And that is private enterprise in space. So through companies like SpaceX and Elon Musk, the cost of access to space has dropped absolutely phenomenally. And with the Starship coming along, we are talking now about $1,000 perhaps per kilogram, as opposed to $20,000 or $30,000 per kilogram. And that's the game changer. Because if we can get the costs of every kilogram down that way, we can afford to launch the tons and tons and tons of material that would be needed to construct a power station in space. In fact, to construct many. And now China, India, Japan, the UK and Europe also are looking at this very seriously, as indeed are the Americans again. And Britain is, in terms of climate change and net zero, is doing well in a way. We have been one of the first countries to simply get rid of all our coal. And I shed a tear the other day because I actually worked at Ratcliffe on Solar Power Station and I saw it built in, it came on stream in 1967. I remember watching it being built. It was not too far away from where I lived. And I went to work there in 1979. And so I have a sort of fondness for a particular boiler on that power station, but it's no more, and there is no more coal burning power stations in Britain. But we want to get to net zero by 2050, and that means getting rid of carbon from our electricity generating plant by 2035 is what the government are talking about, although some people are talking about trying to do it by 2030. Well, this is going to be a huge challenge because right now what we've done is we've filled the gap with natural gas. Natural gas can be burnt in a turbine, produce electricity quickly, and it fills in the gaps when the sun isn't shining, when the wind isn't blowing, or when the wind is blowing too rapidly. And at the moment, we're getting away with it because we're buying more gas. But rather crazily, in my view, we've got rid of our own gas mining. So what we're doing effectively is we're buying in very expensive energy. So these graphs here show you why renewables themselves are not a complete answer. They are important, they're part of the answer, but they can't ever be a complete answer because they're not reliable. You can't have power when you need it. There are times when the wind doesn't blow, and that's shown here, and it has to be filled in by what we call baseload power. And up to now, that has been coal, some nuclear, and mainly gas. Now it's going to be a tiny amount of nuclear and mainly gas. But our nuclear power stations are at the end of their lives too, because we haven't invested in them. And so now we're going to have to start building them again, and it's going to be very expensive. So we've gone from a net exporter of energy here in around about the turn of this century. We were still exporting energy to Europe. Now we buy our energy in very expensively. And here you can see our installed capacity in terms of power and in terms of energy and how it compares with what we actually use. So people get very confused about gigawatts and gigawatt hours. They're not the same thing. One is a power, which simply tells you the rate at which you're using electricity. What's important is energy. So you can see if we add up those numbers there, we're of the order of 100 terawatts hours of energy is potentially available from our renewables, but we need 340 terawatt hours permanently. So to get that, we need to at least triple, and because the population is growing, probably quadruple or quintuple the number of wind farms, the number of solar array farms across the country, which means getting rid of our agriculture and, you know, vying with land usage with everything else we want to use the land for. So the previous government asked again, is it possible that we might do this not by building solar farms on the ground, but by putting a solar farm in space and beaming the power? Would that make any kind of sense? It sounds implausible, but so they asked Fraser-Nash to look at it, and they did. And they did a complete study, literally a system end-to-end study, including all the national grid aspects and the actual practical delivery. And astonishingly, they found that it was not only feasible technically, but it was actually a cheaper way of providing baseload power than the current methods, including nuclear. And so they took for their basis a power station that can produce 2 gigawatts direct to the national grid. So that's about the same as a typical coal-fired power station. And it's a lot of electricity. And to get 2 gigawatts delivered, you need to generate 3.4 gigawatts in flight and beam that down with microwave energy, actually just in S-band. And the rectenna on the ground would be similar in size, just a little bit smaller than a wind farm. So here's one, for example, in the Thames estuary we might propose. Now, people worry about radio beams. People, worry about mobile phones and phone masts, which they don't need to. The energy in this beam, the energy density is quite low. It's 245 watts per meter squared. In other words, it's about a quarter of sunlight. So it doesn't have any consequences for birds and animals and humans, even if they were exposed to the beam. And the beam, of course, would be controlled. So they looked at 3 systems: the British system called Cassiopeia due to Ian Cash, an American system called SPS Alpha due to John Mankins, and the Chinese system called MRSPS. And they all have different characteristics. I'll talk about Cassiopeia because it's an interesting thing. It would be 2,000 tons. The antenna itself would be a phased array antenna 1.6 kilometers across. These are huge numbers. And the rectenna on the ground would be 5 kilometers across. But actually, it's very simple. It's kind of wire and dipoles. It would be transparent to light. This is it. It's a wonderful system. It's going to be very complicated, and there's a lot more work to be done on it. But essentially, you've got a phased array that steers the beam, so the beam is always pointing at the rectangle. And you've got these solar cells shown here as little dots. I think they probably won't be like that in the real thing. But that's Ian's design. It's very clever, but I think it's going to have some challenges. John's, by the way, these are the mirrors that direct the light on. So the whole idea is that the light from the sun is always directed and the beam is always controlled to point down at the Earth. John Mankins' idea is more conventional. It's got steerable mirrors, they're known as heliostats, but it's similar in size because the physics just drives you to these sorts of sizes. A bit heavier, 8,000 tons, everything else about the same. The Chinese design, this one is really like an overgrown communication satellite. The challenge there is going to be, how do you get gigawatts of power through a rotating joint? But this is even heavier, so it's not the most efficient system, though to be honest, they have other designs which are better. Anyway, Fraser-Nash did the study. The British system actually came out slightly better than the others, but there's not a huge amount between the American and the British design. But this graph is interesting. Look at the cost of first-of-a-kind nuclear power. That's what we call the levelized cost of electricity. And you can see that space-based solar power is much less. So that's the thing to compare to, because this is the baseload power. Yes, the electricity from renewables is relatively cheap compared to these, but that's not the point. The point is we're replacing the baseload. We'll still have the renewables on the ground, but we're replacing the baseload. John did the same analysis independently in America and got the same result. So we've set up a space energy initiative to look at this. I sit on the technical committee for that. The previous government went out to places like Saudi Arabia to get them, investment, and there was strong interest to invest in the UK to get this going. And out of the Space Energy Initiative, a company called Space Solar has come, and out of Fraser-Nash, which is now actively working towards this goal of demonstrating a first-of-the-kind big station like this by sort of 2035 is what we hope. Europe is just about getting its act together. They're doing paper studies, but they're also interested now. China, you might imagine, is not only doing paper studies, they're doing actual physical experiments. They say they will do a first-of-a-kind experiment in space in the next year or so, and I would believe that they're pushing ahead in space technology so fast compared to the West. And Caltech, my colleagues at Caltech in America, have actually demonstrated a bit already, and they launched a really neat experiment to test new solar cells and to test deployables. This came from my colleague Sergio Pellegrino, and you can see it there all unwrap from a compact form, and that's how it would deploy in space. And that actually worked in orbit, so congratulations to them. So, got like 3 minutes maybe for questions, but thank you very much for listening. I'm happy to take any questions.
Okay, Craig, thank you very much. If we can give him a round of applause, because I don't know about anybody else, but I found that very interesting. And so, yeah, we do have about 3 minutes. So does anybody have a question?
Hi, Craig. Very interesting. I was just curious, what do the necessary orbits look like to have this thing, in sunlight and also in sight of this rectangle on the ground?
Good question. I should have said, of course, the main one that we're considering is geostationary orbit, because, of course, the ground is always in range then. And when you really think about it, because the geostationary orbit is in the Earth's equatorial plane, it's tilted with respect to the Earth's orbit around the sun by 23.5 degrees by the obliquity of the ecliptic. And that means that except for 90 days of the year, it's in sunlight 24 hours a day. That's why it's baseload. So it's permanently lit. And only around the equinoxes, around the spring and the autumn equinoxes, do you get any eclipse at all. And the longest eclipse is only 72 minutes. So for that, you could just then switch to another power station just slightly at a different angle and get the baseload power. Probably the first experiments will be done in low Earth orbit, and it would be much less power. It would be a demonstration kind of mission. And we've also considered intermediate orbits where by a small constellation, we can provide power from one spacecraft into Europe and then into America and then into China and then back into Europe again. So there are a number under consideration, but GEO is the main one, I would say.
Okay, thank you very much. Next question.
Yeah, just a quick one. So why 2.4 gig band was chosen? That's the maximum of the water absorption, as I know.
I'm sorry, because you're away from the microphone, I didn't quite catch that.
Yeah, I'm asking why 2.4 gig band was chosen, because that's the maximum of the water absorption.
Why 2.4 gigahertz?
Yeah.
For the study, just because it's one of the available frequencies potentially for this. In fact, the frequency now being considered is closer to 5 gigahertz. So that was just for the purposes of the study.
Okay, we're running to time, but I think we'll try to take a couple more questions at least.
Do you have a figure for end-to-end efficiency of a space-based system?
Yes,
sunlight to
though
grid.
I can't recall it directly from my memory. But I basically gave you the end-to-end efficiency in terms of the power. So by generating 3.4 gigawatts in space, we get 2 gigawatts delivered to your house. So it's pretty high.
Hi, Craig. A slightly off the line question. How does it compare with, for example, getting 3 large systems in the desert, which will be permanently illuminated, and then shipping the power around the Earth without actually doing it from space? Why do it from space when you could do it on the Earth, in other words?
I'm sorry, because again, you're away from the microphone. I couldn't quite catch that. Why are we...
Why do it in space
Yeah.
when you can do it on the ground if you were to put some stuff in deserts that would give you 24?
Because
so
we
need
have
several
something
of
called the
them.
day-night cycle. So for half the day, the sun doesn't shine, and also we have clouds. So actually, for all the power installation in Britain for solar arrays, you can only ever get 10% of it, potentially.
Yeah, my question didn't quite come out, sorry, Craig. The idea was to have them distributed around the globe, around the places where you do get good sun.
The satellites would be distributed around the globe, yes. So there would be, it's, by the way, it's dispatchable power as well. So the beam can be switched very rapidly from one place to another. So, for example, it could be powered into Europe at night when we need it. And then in the daytime, it can be diverted to somewhere else.
Okay, next question.
Given the number of things wanting to occupy geostationary orbits, has someone done a number for sort of how many of these massive structures you could fit in the geostationary plane? So
I think your question is, what about the overcrowding of the orbits? Yeah, it's an issue. And in fact, one of the environmental impact studies that is underway is looking at that, because these are big structures. Obviously, I mean, roughly speaking, we're talking about an object which is the size of a small city. It's 5 kilometers by about 2 kilometers across. So yes, that's going to be one of the issues for the use of geostationary, and also, of course, getting the frequency allocation agreed internationally is an issue. But also, we don't want the VHS Betamax problem. We want all the systems out of China, America, Europe, India to be compatible with each other, so that we can all share the power as well. So that's a legal thing. It's already under discussion with the United Nations to try and get that sorted out.
Okay, we're running a little over time, but I think we'll take one last question.
Hi, Craig. Thank you very much. Very interesting talk. Thinking back to your cadmium telluride in-flight experiments.
Yeah.
And you found you had a degradation of output power over time. Reminds me of a case we had, must have been in the early 2000s, of the problem where cover glass for the solar cells was glued on, and the glue turned opaque in space. So I don't know if you remember those cases. But yeah,
I don't remember them, but I can well believe it. It is an issue,
it was a major thing, and there were three geo satellites affected by it. I wondered if it may have played a part in your tests at all.
No, you see, well, the testing showed that it was the shunt resistance that was changing rather than any other form of degradation. We very carefully modelled all the different ways it might be changing, and that's the one that fitted the best. We used proper space-rated glue, but it's a very interesting point, because there are a number of companies at the moment who are trying to do space cells on the cheap and use terrestrial type glues and terrestrial type solar cells, and I'm not sure they're really aware of those kinds of issues, because they definitely are there. So yeah, you can be caught out. But actually, my colleague Stuart did a very careful analysis of it, and as far as we can tell, it's the gold migration fits the degradation seen best.
Okay, once again, Craig, thank you very much, and thank you for spending an extra 5 minutes answering questions. And hopefully you'll come back and give us an update at some point in the future. So if we can show our appreciation once again to Craig.
Thank you very much.
Okay, we are running about 5 minutes late, folks. So in approximately 10 minutes, we'll be having Dave Johnson give us a FunCube update. Thanks again, Craig.
Thanks, Ian. All the best.
You too. Bye-bye.
Goodbye, everyone.
gives me great pleasure to reintroduce Dave Johnson, who's going to give us a FunCube status update.
Thank you. Well, good afternoon again. I'm wearing my presenter's hat this time, not the ONSEC. There's going to be a bit of a surprise in a few minutes. I've had a box handed to me. FunCube and what's happening next. David's already alluded to one project, so I'm going to talk about another one. For those of you who don't know about FunCube 1, launched in 2013, 11 years ago, and still operational. You can see how big she is, 10 centimeter cube, 1U and a 3U launcher with a spring at the bottom to push it out. Our friend Wouter actually working on it in its assembly all those years ago. We've got lots and lots of videos on YouTube about this with the antennas springing out, etc. Thanks to Mr. Heck many years ago. Oops. Hang on. Current statistics. She's been in orbit 11 years. Raw packets transmitted in that time, just short of 69 million packets of data. We've received just short of 12 million of those, which is about 17%. The packets are transmitted at about every 5 seconds. That's where the maths come from. 24 of those packets actually make up the whole orbit data. The whole orbit data is basically the heartbeat of the system, the battery, the charge, the spin rate, etc. Over that time, we've had an awful lot of people presenting data to us in the warehouse. The maximum for FunCube 1 itself is about 1,400 people. That's not the whole number, because we've also had Naive 1 and JY1SAT, and they've contributed to the warehouse as well. I say 1,400. Amateur radio operators are competitive. I'll show you a slide in a couple of seconds in terms of how competitive they've been. But for each of those packets we've received, we've probably actually received more than one instance of that packet. Current number is about 36, so it's dropped quite considerably. I'll explain about that in a second. But we are still getting real data and really useful data. The FunCube family. Oscar AO 73 was FunCube 1, of course. Launched about the same time as UCube 1, a UK Space Agency satellite with Clyde Space. We also were involved with another set of projects for ESA education, which is where EO 79 came in. Part of an interesting fact that's with FunCube 1, because we're not for profit organisation, IC Space were approached twice for designs for CubeSats. Have you got anything off the shelf? Well, no, we haven't, but we know somebody who might have. So we licensed the design of FunCube 1 as EO88 and JO97. I'll tell you a little bit more about that in the next set of slides. SAO, the European Student Earth Orbiter, is another project that we were involved with, and some of our payloads went into that in the same way that David's explained that FunCube Lite is carrying other payloads. Reliability, we've been quite good. Everything fails, of course, eventually. AO73 is still alive and well. We're having some problems with the EPS, so we're actually having to actively manage FunCube 1. UCube 1, it's the UK Space Agency in Clyde Space, lasted just short of 4 years. It's had battery failure. EF-79 from the von Karman Institute, end of mission, negative power budget was one of the side effects we had from it. EO-88, Naive 1, is still going and is active after nearly 6 years. JO-97, JY1 sat, microcontroller failed, probably through radiation damage. And SAO, multiple design issues on the platform is all I will say. It was a student mission, lots and lots of things that could have been designed a little better right from the outset. But we got it up there, and it had a short lifetime. Again, it's a repetition of that slide. We have flight history with all those satellites for 22 years. So I think AMSAT-UK and the FunCube team can be extremely proud of that. David and Wouter and Duncan and Jason and Phil and others have been involved with all the boards we've actually built on the FunCube system. Some of them, as David pointed out, are actually being reused and rejigged into FunCube Lite. Extremely reliable. Most of our stuff has actually worked extremely well. We've had problems with some of the commercial off-the-shelf stuff, which we believe the EPS is one of them within FunCube, but it's still going. It's still providing power. We still run the data warehouse, as I've said, with just 36 uploaders. We have some extremely regular ones, and N7RED is in the audience here, I believe. There he is, waving away at me. Thank you, Andre, for that. The interesting number, if I can get it, is that one is the battery voltage. It's sitting max at about 7.9 volts. And we can get the min and max data over a few days. It's been up at about 8.4 volts, I think was the maximum we've ever had. It dropped down to about 7.2 before we started actively managing it. And it's quite happily sat at just below 8 volts. We've had to make some compromises because of that. Next slide, I think may show it. But you can also see we've got a significant number of packets. We did have something that caught us out because we've got every packet has got a serial number against it, and we rolled over the number of units. We rolled over the bits. So the warehouse got confused for a few days until we scratched our heads and worked out why the sequence number reset. So we had to do some trickery with the warehouse to actually catch up again. So what had been the original epoch in 2013 to actually make all the numbers work, we had to reset the epoch to a couple of years ago. But we've still got all the data, we've still got all the real time, we've still got all the WAD. But if anybody wants to do a PhD to recover it, we'll have to do some trickery to actually get the satellite time out. Mentioning satellite time, the onboard clock is just a crystal. And of course, it's drifted over time. And I think we're probably about 10 days out from what the real time is. But the average, we can actually do all the math with it. What else we got? We're still getting good whole orbit data. And the whole orbit data is the 95 minutes from an equatorial pass to the next equatorial pass. From that, you can see when we're in sunlight, when we go into eclipse, and then we come back out of sunlight again. And the magic line is just about there, which is our 7.8 volts. And we only ever drop down to about 7.7 when we're in full eclipse. We've had some interesting effects in this over the years. We've actually seen solar eclipses as we've gone behind. I think we've seen about 3 in its lifetime, just a tiny drop as it's gone into eclipse. We also track the where we are at any point. We've got a Keplerian Elements bit of software running in the background. So whenever we capture a piece of real-time data, we actually capture where the satellite, what the subsat point of the satellite was. Our friend Colin in Australia has been collecting data for more years than I care to remember, and every 2 weeks or so he gives us the spin rate. You can see it's averaging about 3.6, 3.7 there. We've had it down to 2 seconds spin rate. Trying to get telemetry from it at that spin rate is something of a challenge. We still get it, and trying to command it at that spin rate is also a challenge as well. But we've succeeded. Now this is an interesting slide. This is how the spin rates changed over time, and we would love to know why this changes. It's gone from, you've got 9 seconds there down to 2 seconds, which is our worst case. Is it cyclical? Is it related to something to do with solar radiation? One of the things we've talked about within the team is, because we've got electrical currents flowing through the satellite, are they actually reacting with the magnetic field? And are we seeing some oscillation because of that? But it's long-term oscillation, and that just feels like it's a typical thing that a PhD student might like to look at. We've actually offered the data to students at University of Surrey to actually run some AI against it, see if they can analyze it. We're still waiting, is all I will say. I said that amateur radio operators are competitive. This is the ranking for all the satellites in the family, and I've just highlighted FunCube itself. Where are we at? 1.62 million for HB9 MFL, and I think Mike's up there somewhere as well. G4BIP is one of our main contributors in the UK at the moment, and Brian's coming up the list slowly. I'm down there somewhere. The trouble is, because I test the warehouse, some of my numbers get somewhat skewed, so I never claim anything for it. But you can see that that number there, we've had maximum uploads we've had have been about 2,500 users. Some of them they've only contributed, just for play. Let's contribute 5 packets. But the big players are up there. And Colin is there somewhere, our provider of our spin rate data. We're still doing fitter messages. We still give the opportunities for students and other organisations to upload fitter messages. We've got some advertising, of course, and a bit more advertising. We even try a bit of French as well. If anybody wants to upload request for a fitter message, please email operations@funcube.org.uk, and that will end up in my email box or some of the other operators. Moving on, David's mentioned FunCube Lite with the sort of space south. We are thinking about, and we're more than thinking about, the next generation of FunCube. I did a presentation 2 years ago and I called it FunCube Next, and it was going to be a 3U CubeSat. We've reduced our scope a little bit and it's going to become a 2U CubeSat. I mentioned Icy Space and Naive 1 and JY1Sat. They were not quite licensed, but we were given the opportunity to have parts in kind. They built the devices for the two organisations that that licensed our devices. So we were offered the opportunity to acquire components and the opportunity for Icy Space to assemble anything we actually came up with. We are in negotiations with the moment in terms of what we can acquire for free and what we have to buy. And on this little desk here, there are two devices which has just been put in my hand: the engineering EPS and the Magnetorquer. So I've already opened this box once today, but I'm not going to go any more than opening this cardboard box. And I'm not going to open this because I haven't got any earth straps on me. But this is the EPS and it's the Magnetorquer. So we've actually been delivered this today. So we're very, very proud. We're very, very happy. We're very, very pleased that Icy Space have actually honoured that part of the deal. What we have to do, because that doesn't cover everything, of course. We have to purchase some equipment, this is part of the purchase. But we also have been honoured in that they will be providing flight hardware for us as well. But as time's gone by, of course, that original negotiation was at a certain price. Things have gone up, so we may have to actually make up the difference, shall we say. I won't go all through this because this is all on the website, etc. But in principle, we've gone from this was some of the original specifications. We've gone from 3U to 2U. We've gone from 3 transponders to 2 transponders. Camera, yes, maybe. On X-band, maybe. But it will. Some of the things we're actually talking about, we're still talking about to our software engineers, is fly your own code as well, actually for the ability to upload data. One of our friends in the audience is also talking about possibly an SDR experiment on board, and we're also talking about high bandwidth downlink from the satellite. But it will be the same principle that FunCube 1 and all our other satellites have been. It will be for STEM outreach. You know, the standard FunCube that we had, that we still have, I should say, the FunCube software and the data warehouse. It's going to still roll into this system. As part of this, we would like it to be a UK registered spacecraft. FunCube 1 became a Dutch, and thank you to AMSAT NL for helping us with this. FunCube 1 is actually a Dutch satellite, not a British satellite. We have to apply for a CAA orbital license. The CAA are now responsible for orbital flight now. And if we go abroad, we have to apply for other licenses as well. If we go for a non-British launch, if we go for something like SpaceX or other organizations, we've got to apply for a different license as well. One of the things we have to do with the CAA is they triage us basically in terms of is it worth you applying for that license. So they do something called the red, amber, green test, and basically it's, you know, what's your worthiness? Do you have any flight heritage? Who are the people involved in the project? Who are the people backing the project? And that's basically what the red, amber, green comes from. We put our application in, I think, probably about 4 months ago, maybe a bit more now, and we got an orange. So we couldn't get a red, so we couldn't get a green because we couldn't specify who the launch provider was. But as far as the CAA were concerned, we can go ahead with a full application. That's my job as on-sec in AMSAT UK, representing the FundCube team as well. We also have to apply to Ofcom to file for operations in space in terms of the frequencies we're going to use. That's another task for me as well. But we know a lot about that already, because some of our friends in the audience are responsible for the ITU filings for amateur radio satellites. But even though we know that process, there is an overlying process that we've actually got to apply to Ofcom for frequency filing for space. As you can imagine, we have to also apply for insurance. If we smack into something, another orbital asset, and there's going to be some monies to be paid. So we're talking this week. I'm starting to talk to insurance brokers. I think I've got about 5 lined up at the moment. I've had some indications from the CAA, basically what their expectations are for insurance, but because we are not something that weighs 22 tons in orbit. We're something about a kilogram. But we already know that we coming to close proximity to other assets up there. We get spherical conjunctions, so basically, the probability of where your orbit is and what that conjunction of those two spheres is approaching another satellite. In the past, probably 6 months, Graham's got the numbers in terms of how many conjunctions we've had. So we see conjunction come up, and it's maybe a kilometre. I think our worst case has been 200 meters. But then we see the other body has moved. So we believe it's probably a SpaceX spacecraft, and they've got thrust. We haven't. So the CAA, obviously, risk mitigation and debris mitigation, we need to take insurance out. I've gone slightly out of step here. We want to put a camera on board FundCube Plus. Still under debate at the moment. As David said, with other spacecraft we've uploaded stored images. So our software engineers are basically looking at what's the best way to get data down from us. Our friends at SSTL have done some work with Raspberry Pis to get data down. So we're talking to them. Probably a lot of you know Chris Bridges. Chris Bridges is involved with a lot of our projects. And thanks to David Bowman, etc., there's a lot of work going on in parallel between FundCube Lite and this particular project. So there's a lot of crossover between the two designs. David talked earlier about his radiation sensor. We're going to fly that on FundCube Plus. If I say FundCube next, excuse me. FundCube Plus is going to fly David's gamma ray detector. It's been tested on the bench. I'm sorry, David, if I've stolen one of your slides. Tested basically with a laboratory set of emitters, and that's going to work extremely well for us. Again, as David said in his previous presentation, we have a set of telemetry blocks that we send down in terms of the real-time data, whole orbit data, FITA messages. We may change those to actually allow for the transmission of this data and the images as well, because we know we've proven that we could do that with JY1 sat. This is going back to what David was talking about, FundCube Live on Jovian 1. The FundCube team have been extremely busy for all these projects. I'm one of the team, and I think there's 7 of us. We meet every Sunday evening to discuss what's going on. It becomes a technical discussion by the end of it. And there are discussions going on during this weekend regarding both projects. We try to get together fairly regularly, as often as we can, basically face to face, to thrash things out. It always gets more intense the closer we get to the actual, to the design and towards launch. I'll go back a step to FunCube 1, which we called KISSAT, Keep It Simple Stupid SAT was our first name for it. And I think the whole gestation of FunCube 1 was probably about 4 years before we actually got to a launch. But one thing I will say to anybody who's actually considering a CubeSat is test it. Test it to death. ISIS always give us the honour to say yours was the best tested CubeSat we've ever seen. That's 10 years ago since launch, and things have obviously got better. But we're really proud of the of how she's still working. I think that's it. I've finished early.
Well, thank you very much, Dave. I think quick round of applause for Dave, and then I think we've got some time for some questions.
Dave, you were saying about 2 transponders, so what are you talking in terms of?
Is David in the room anywhere? Okay. We'll be doing the normal linear transponder, but it's likely we're going to be using UHF and VHF. We're also talking about L-band as well. So yeah.
So you're talking VU?
Yeah. Yeah, so there'll be probably a matrix of some kind on board, but that's to be decided. We've got to, as I said, we've got to go through the IARU evaluation process. So we've got to apply. We've got to write the whole diatribe and then submit that. We're not at that stage at the moment.
Next question. Anybody? Anybody from the stream? I guess it might be an early tea.
It might be an early tea, right? I'm now going to put my other hat on, my ONSEC hat.
Okay.
To say that people have been asking me this afternoon, what time's dinner? And I'll repeat this as often as people bump into me outside as well. Dinner is at 7:30 in the hotel. The hotel have asked us to gather at about 6:45 in the bar, to move through to the restaurant at about 7:15. I believe that places have been allocated on the tables, but I'm sure you're more likely to move around. There'll be no raffle, and there'll be no auction tonight. So it's purely a social gathering. And that's it. Thanks, Ian.
Okay. In that case, folks, I think we can head for an early tea back here at 4 o'clock, I believe. Well, welcome back, folks, for the talk of the afternoon. And Kieran is going to give us an ARIS update for the last 2 years and 40 years of amateur radio on human spaceflight. Kieran, over to you.
Green now. Okay, so hopefully this will just be an update from where we were last year. If you remember, we were sitting here last year with cars and trailers full of kit ready to go down to Broadstairs and to deal with the contact at Matthew Payne's school, and I'll come to that in a minute. But main thing is amateur radio and human space flights. Just so everybody knows, we've had the space shuttle, we've had the Mir, and now we've got the ISS. And there's 40 years worth of history there now with human space flight. And that was a big thing that we wanted to celebrate this year. And I'll come on to that and show you some of the stuff that we got up to. Couple of worldwide ARIS successes for you as well. First one being the 40th celebration. We got everybody together in Florida at the Kennedy Space Center and had an international meeting first of all, and then a conference where we had a number of astronauts come along and tell us about their views and their history and their experiences of amateur radio usage itself, including some very interesting ones of debates that went on between fathers and daughters about dogs and pet dogs being purchased as a consequence of their dad doing a flight on the space station. We've continued to make educational contacts around the world, and as you can see, there's still quite an impressive number, over 1,660 individual contacts now made since we first went live on the ISS. And 2024 is turning out to be quite a busy year for us. We've had 79 contacts so far, and that includes Super Saturday, which was last week, where we had 3 contacts in 4 orbits, and Super Friday, which was yesterday, where again we had 3 contacts on 2 continents in the space of 3 or 4 orbits, I think it was. The ham TV transmitter has been returned to the ISS, which is a great advancement. We're now just waiting for installation and commissioning of the ham TV itself, and that'll bring back the very beneficial thing that we had of being able to see the astronaut and asking him or her to give us a wave during the contact itself. As you've probably heard, the SSTV equipment has been renewed and flown to the space station as well, and that is now in progress of experimentation at the moment, and I think it goes on till Monday or Tuesday. Already we've been having some great reports around the world of the reception that's been carried out and the successful use of the new SSTV equipment. And finally, we've continued with the private astronaut flights on Axiom, and we've had 2 successful flights on Axiom 2 and Axiom 3, and we've got Axiom 4 coming up sometime early in the next year as well. As always, we get judged by the numbers. This is just a splash. You can see we've got most of the US covered, and we've got 75 countries, including Antarctica, now covered in the UK, sorry, in the world for contacts that have taken place. One that I do want to point out is that because we're all volunteers, we've estimated that there's about $5 million worth of in-kind support carried out each year by the volunteers of ARIS. And when you see the contacts that go on, you can understand there's quite a lot of effort involved with that. back last year, I showed you this chart showing the breakdown of participation and the total figure of just shy of 185,000 impressions or people reached for ARIS contacts. We've had that updated this year to include 2023, and as you can see, we're just shy of 210,000 people being reached by these contacts. And that's just showing what's happening year on year, and that the number of people we are contacting and reaching with the ARIS contacts is increasing itself. And 2024 is turning out to be another good year itself. You can see some of the numbers up there. We've still got another quarter to go, but we've got quite a number of contacts left to go around the world in 2024. So, to UK successes, as I said last year, we were waiting for going down to Broadstairs to go to St Peter's in Thanet Primary School. That turned out to be an extremely popular and successful contact itself, and Matthew will be able to attest to that itself. We've had the Mrs Ethelstone's Academy in Axminster, which was another direct contact, which I'll come on to shortly. We've had the Eric Knows Charities or Community Interest Company, which was a telebridge, and we've had last weekend the Girl Guide in Surrey. So St Peter's in Thanet had their connection or their contact on the 18th of October last year. John and I arrived on site on the Monday following the colloquium, and got everything set up. Had quite a lot of interactive sessions with the students at the school there, who had already been prepped quite nicely and quite informatively by John Hislop and Matthew themselves. And as I said, there was a real buzz at the school itself. For this contact, we actually had Megan Christian, who is the ESA reserve astronaut in the new intake of astronauts for ESA itself. She came along and was able to answer questions that we didn't get asked, but also to answer questions from the children themselves. As you can see, we had lots and lots of interaction with the students and their parents as well, because the antenna was placed right in the middle of their playground, and John's Jeep, which you can just about see there, got even more interest as well in terms of the size of it and the noise that it made. But I think the picture that for me makes that contact really special is the one of Isabella, and the expression on her face whenever the audio first came through from the space station. And that sort of sums up the reaction of the kids. There was sort of sheer delight, sheer enjoyment of what was doing and what was going on. We then moved on to Mrs Ethelstone's Primary Academy in Axminster, or the Acorn Academy in Axminster. This was another one that was a direct and happened on the 17th of April. The school actually returned from their Easter holidays on the Tuesday, on the 16th of April, and we were there on site actually getting set up while the kids were trying to get back into classes. Again, that was a very successful one, and you can see the delight in the faces of the students themselves. We then went on to Eric Knows charity, or the Community Interest Company. This was a telebridge, so something that we don't normally carry out. We prefer to do the direct contacts in the UK because of the impact and the impression that it makes with the children. But we carried out the telebridge. I was actually in York, having had my first grandson born a few days earlier. And we had the UK Space Agency also joining us. Eric Knows was or is a charity for neurodiverse children, and it provides a lot of support for adults who've got children with neurodiversity. And one of the things we were able to do was get hold of somebody from the UK Space Agency who is neurodiverse, and we got him to talk to the students as well about careers in the space industry and how to work the neurodiverse characteristics into a successful job application itself. That then turned to last Saturday, the Girl Guiding in Surrey West. Another direct contact, one that we spent a couple of days setting up at the Brooklands Museum in Surrey. Focused primarily on the girls and the young women of the Girl Guiding Institute. And we managed to get Sunita Williams as the astronaut, so trying to keep an all-female theme with the contact itself. It was high profile for us because we had the Duchess of Edinburgh in attendance at the contact, and she made a greeting message to the astronauts and also asked one of the questions. And speaking to her afterwards, she commented that she had so many other questions that there just wasn't enough time to ask them. Again, Megan joined us for the contact itself and took part in a very lively Q&A session with the girls. And the contact itself did have its own moments. We had a very late notification, something like about 36 hours beforehand, of a change of time. So we were actually on site. We had got most things set up. And then at roughly midnight, a day and a bit before the contact, I got notification that NASA wanted to change the time of the contact itself. So we had to make some hastily rearrangements. But all in all, it was a very successful contact. And looking at the social media hits and impressions that are done for ARIS International just on its own, normally we have about 2,000 to 3,000 such hits per contact. But with this contact, with the mention of ARIS International, we got something like 180,000 different contacts, different impressions being made. The day was purely towards the girls themselves. They had an awful lot of activities carried out as well as the contact itself. And I heard a quote this morning from one of the RSGB staff who was present, who said that one girl at the very beginning sort of questioned why she was there, in the sense of why are we here, because this is all boys stuff. Come the end of the day, she was asked again, how did she enjoy it? And she says it's absolutely fantastic. She thoroughly enjoyed it, and why shouldn't the girls have so much fun in the contact and in the STEM type activities? The girls were very enthusiastic. The question and answer session went through really well, and Megan, who took part in it, really came through with some really good answers as well. And that's Megan herself just answering some of the questions. I mentioned last year we're still on the lookout for ARIS contacts in the United Kingdom, and I do have a document that can be sent to you by email if you're interested in pursuing an ARIS contact, to give you lots of details in terms of what to expect, what to do, what learning resources are available itself. And my email address is just there, so please feel free to email me, and I'll send you a copy of it. But perhaps the main thing that has happened this year is the 40th celebration. So back in 1983, on STS-9, it was Owen Garriott first took some amateur radio equipment up with him to experiment in his spare time, and it was made clear that he wasn't allowed to do this in program time or anything. It had to be his own downtime. But he ignited an enthusiastic response from amateurs on the ground that has helped sustain amateur radio on human spaceflight for the last 40 years. And what we had was a bit of a celebration. We met up at Kennedy Space Center in Florida and had a wonderful couple of days doing, first of all, a face-to-face meeting, and then sorry, the words just escaped me. A conference for the actual event itself. Like I said, Owen Garriott made the first contact in space on STS-9. His son Richard was there as well and gave us quite a detailed overview of what it was like to be a child in a family where the father was in space, both for the Skylab missions and for the STS-9 missions themselves. But we've managed to find a recording of the very first contact that he did. Oops. Let's see if I can get this to work. No, it's not going to work. Sorry, I'll dig it out later. And if you're interested, there is a recording of the very first contact that was made itself. The bulk of the meeting took place on the first couple of days of it, where we had an international face-to-face meeting. More than 50 delegates and attendees joined us at Kennedy Space Center and took part in some of the discussions. Frank Bauer mentioned, the chair of ARIS International mentioned that he considered it to be a historic meeting itself, because it represented 24 years of ARIS operations, 30 years of planning for amateur radio on the International Space Station, and 40 years of actual operations with the shuttle, the Mir, and the ISS itself. Frank liked to emphasize the fact that ARIS is an international body, and international actually forms our middle name, or part of our middle name, and was very proud of the impact that the program has had throughout the world, and for the amount of worldwide support that is given to it. The focus of the meeting was primarily on the strategic directions for 2024, and these haven't changed much since 2023. There's still the improve, the expand, and the reduce focus that Frank wanted, but the additional part was to celebrate the 40th anniversary. But he started out, first of all, by remembering how ARIS came about. And I've talked of the shuttle, the Mir, and the shuttle and the Mir experiments that went on, and they were carried out by a number of different groups around the world. But NASA, in the form of Pam Mountjoy, challenged the amateur radio community back in the early 90s to come together as one voice and provide the amateur radio facilities on the International Space Station. Pam was an educator at NASA who very much believed in outreach and pursued outreach activities quite heavily, and was very surprised when initially she thought, and her colleagues in NASA thought, that the worldwide amateur radio community couldn't come together enough to make an organization actually came up with the what became ARIS, and the rest essentially of that is history. We then talked a little bit about the engineering update. The bulk of it was to do with AREX, the amateur radio exploration of the lunar surface and the lunar orbits. And this is the halfway house to getting to Mars, which we're looking towards. And we focused a lot on operations both on the moon itself and on the gateway, the lunar gateway that's proposed as well. A major part of the discussion involved the frequency coordination that had to go on because of it. Because the ITU rules don't apply on the moon or in lunar orbit, there's a working group that pulled together the frequency requirements of all the different bodies, but also the desire to keep certain parts of the moon quiet itself. And there's something called the quiet side of the moon, and the lunar gateway, we found out, actually progresses around that particular area of the moon, and that limits the different frequencies that we're allowed to use, both up and down itself. So we had quite a significant discussion on what frequencies we could use and what we couldn't use themselves. We also had an update on ham TV. I've mentioned that it's already gone back up to the International Space Station. The system has gone up now with a new 8-pole filter between it and the antenna, and that has been a requirement of NASA because of new frequency spectrum coordination requirements actually on the space station itself. We also talked a little bit about the digital communicator, which Phil Crump from BATC had presented last year at the colloquium, and looking as a potential successor to some of the radio equipment that we've got, stroke maybe even for use on the lunar surface and the gateway themselves. Associated with that, there was the question of antennas. And if you're interested, I've got some photos which I can show you later on, which show the design of an antenna hat, which is made up of a number of patch antennas, which is designed to go onto the lunar gateway. And one of the patches will be facing the Earth at nearly all times, hopefully. And then the last thing that we were talking about was the potential for remote controlling the D710 in Columbus. This is something that we've had as a desire for quite a long time. And one of the attendees, Chris Thompson, G0 something LK, I can't remember it, sorry, who lives over in the States now and in Canada, has come up with a mechanism of being able to control the D710 through the use of PACSAT communication protocol. And Chris was able to demonstrate switching the D710 between the voice repeater and between SSTV activities, uploading pictures on SSTV, scheduling different SSTV transmissions, and has developed something that is potentially really groundbreaking for us, because it starts to remove the need to have the astronauts involved with reprogramming or repurposing the radio into different modes. We also had the opportunity to have a look around the KSC Space Center site itself, and we were given a special tour of something called, it's listed as the International Space Station Processing Facility, but it's now actually called the International Space Systems Processing Facility. But it's basically the large rooms where they prepare all the spacecraft and everything else for space flight itself. And it's a room that is big enough to actually fit the whole of the International Space Station into at any one time. And that was really special. We had also another visit out to Launch Complex 39, both A and B, where all of the Apollo and all of the shuttle missions have taken place or have launched from. And we got a very close-up view of it indeed, and it was really special. And none of us realized that there was actually a monument or a monument to all of the flights that have taken place. And SpaceX now fly from Launch Complex 39 as well. So on to the anniversary conference itself. We had our guest speaker was Richard Garriott, and as I said, he recounted a lot of the time when he was a child, when his father Owen was on the Skylab space mission or on STS-9, and had brought along quite a lot of updates in terms of and memorabilia for the contact itself, including the radios that he used and some recently discovered tapes of the actual contacts taking place from space. And one of the things Richard was wanting to do was get those digitized and made available so that everybody could go through them and potentially listen to see if their calls were registered in 1983. He also talked a little bit about his own space flight experiences and the contacts that he made in around the world when he was on the space station. And one of the things that was really nice was his acknowledgement that the contact that we did at Budbrook in Warwick in 2008 was one of his favorites because it was one of the most well documented contacts that he had actually seen at that point in time. And that was an opportunity I had to meet up with him again and chat with him. But he went through some of the trials and tribulations of getting to space, the numbers of times that he had booked tickets onto space flights or had founded companies specifically designed to take people up to space, and also recounted some of the things that he set himself through, such as major surgery, in order to pass the medicals just to be able to fly on the Soyuz when he did. So the conference itself continued with the journey to space. So Frank and a panel of people went through the history of how the first amateur radio was actually allowed onto a human spaceflight vehicle, and was able to demonstrate and to produce some of the original documentation that went back and forth. And it's quite interesting to learn that Owen Garriott actually tried really hard to get it onto Skylab as well, but was unsuccessful. And it was only whenever he was assigned to STS-9 that the idea became a reality in getting equipment onto the space shuttle itself. A lot of time was talked about SAREX, SAFEX and MIREX. SAREX is the Space Amateur Radio Experiment, or the Shuttle Amateur Radio Experiment. SAFEX was the equivalent carried out by the German DLR space agency with the Skylab, not Skylab, sorry, with the, yes, I think it was no, it wasn't Skylab. It was another laboratory that flew in Columbus. And MIREX, of course, was the amateur radio experiment on the Mir space station. And that developed into a discussion of the usefulness of amateur radio itself. And a lot was talked about the use of EMCOM, or emergency communications, when the Soyuz vehicle, or the Progress vehicle, sorry, crashed into the Mir space station, and how much it was the amateur radio equipment was used. A little bit of legacy, because we carry on the emergency communications role now with ARIS, and have stations around the world ready to react to mission control whenever they request assistance. We discussed a lot about STEM and STEAM outreach and the importance of it itself, and the NASA opportunities that we have to practice STEM and STEAM outreach, especially on the Artemis missions themselves, which are the next stage of space flight that we're looking forward to. And any celebration can't go on, or any meeting of people who are celebrating an historic thing such as 40 years of amateur radio and space flight couldn't go by without having a special gala dinner. And this was held this time at Kennedy Space Center underneath one of the last remaining Saturn V rockets, which was impressive. If you've never seen it, or if you've never been to Florida, to KSC itself, it's well worth a visit. The rocket itself is absolutely enormous, and we had the people that dress up in Star Wars outfits all come along and greet us whenever we first arrived at the gala dinner itself. But there was one special moment in the gala dinner, and that was when Lou McFadden, W5DID, was awarded a special prize, or a special recognition for all the work that he's carried out for ARIS over the last 40 or so years. Lou's had a very long and distinguished career in NASA, working on the Apollo missions and on the space shuttle missions themselves, and has had a hand in just about any and every piece of radio equipment that's gone up there to support amateur radio. The final day of the conference itself sort of focused on the transition from SAREX, SAFEX and MIREX, which had a very different mode of operation. The SAREX missions were always done, and the contacts that were carried out in SAREX were always done on the basis of mission elapsed time, which was always a challenge, especially whenever the shuttle got delayed in its launching itself. And talking about the transition from mission elapsed times, when it was sometimes unpredictable as to when the contact would happen, to the more regularized pattern that we have now with ARIS, where the contact is actually planned for a date and time itself. Shin Atwa from Kenwood JVC, who was the designer and developer of the D710, was also there, and he gave us an intriguing history of Kenwood radios in space, and also shared a little bit about the developments that took place to develop the new IORS, the interoperable radio system, most of which took place whenever we had our international meeting in 2016 in Houston. And Shin was working through the night to send stuff back to Japan for them to test things, for them to send it back to Shin itself, and the result was the new radio system, which gives us the extra power for contacts. As I said, the ham TV was discussed as well, and I took part in a panel session where we discussed the use of ham TV and how much it enhanced a school contact. And we were looking forward to actually getting ham TV back up onto the station so that the contacts could resume. And there was then a a review of educational experiences. So a number of teachers, and just out of interest, are there any teachers or lecturers here today? No, okay. About their experiences of carrying out ARIS contacts themselves, and how much they engaged and enthused the students themselves. And the whole event sort of wound up with a special link up with the ISS, with Laurel O'Hara, and she was able to ask, or we were able to ask a number of questions of her and get a contact in the books for that particular one. We also had some of the international mentors who look after the schools and look after the contacts take part in a panel session as well, where we recounted the efforts that have taken place over the last 23 years themselves. And the graphic you can see on the left is something that we developed during the course of the conference itself, but each little dot is a contact that has happened around the world since November 2000, when operations first started on the ISS themselves. And as you can see, we've got the lone one on Antarctica, which concluded the activation of just about every continent in the world for an ARIS contact. And then we concluded the whole event with a review of pioneering activities that amateur radio has actually been involved in, from the likes of SuitSat, which was the space suit that was thrown out the door itself and attracted much attention, which has then gone on to develop the deployment of small CubeSats from the space station as well, to talking with families and friends over the radio, to now seeing other parties in the space agencies do similar sort of activities themselves. And we rounded off with a look in terms of what amateur radio would look like on the Artemis missions themselves, and how we would fit into the Artemis program. And a lot of interesting discussions were taking place with a number of NASA folk who were there. So that's a bit of a whirlwind sort of run through everything that we've done. But all in all, it's been a really busy year. 4 contacts from the UK is pretty much unexpected, but something that developed itself. We were really glad we had we started off with the Broadstairs contact itself, and that set the scene for Axminster, and then the Girl Guides, and the special one with Eric Knows. We have one more contact coming up, which is again another telebridge, and that is in a couple of weeks' time. And hopefully next year I'll be able to report on how that goes itself. But other than that, thank you very much.
Yeah. Thank you, Kieran. Any questions?
Yeah, thanks, Kieran. Any thoughts about changing or adding to the FM repeater or FM amateur radio style of equipment to SSB linear type of stuff, which opens up a lot more bandwidth? That's the first thing. And the other thing is, did you eat astronaut food at the gala dinner? Because that would have been quite appropriate, wouldn't it?
I've got a picture. I've got to show you this. So let me find the picture. Where have I put it? No, I'm not going to find it. Answering the food question, no, we didn't have astronaut food, but it was very much astronaut themed, and the butter that came out with the bread rolls at the start of it was shaped in the form of a shuttle. So we can claim a little bit. In terms of the bigger bandwidth, I don't believe that we're looking at anything extra on the ISS at the moment other than the FM. But when we move to the lunar gateway and the lunar surface themselves, we're certainly looking at other modes and other types of equipment. Most of it will be SDR based equipment, which gives us the flexibility to change whatever modulation type we want to use. But there's talk of FT8 or FT4 or FT8, looking at SSB as well, side of things, potentially FM as well. But it opens up the sort of that level of detail hasn't been decided yet, but it has opened up the discussion in terms of what we can do and what's possible.
Any other questions?
Thank you. I was just thinking about good old Mir days, and when there was a camera pointing at the window transmitting SSS TV images. Now they're all the same. They just come in batches from time to time. Is there no plans to have a camera again pointing at the window? I understand that inside there is privacy questions with the astronauts, and I respect that, but not at the window. Thank you.
Most of the SSTV campaigns are going to be done on the basis of pre-prepared slides themselves. We do have an SSTV camera up there on the station, which we're hoping we can reactivate and let the astronauts take different pictures and then transmit them themselves. But for now, we're sort of staying with the pre-formatted ones. And getting itself. To do anything different needs a computing facility for the Ares station, and we haven't got that yet. But we're hoping to develop something like a Raspberry Pi solution, which does have cameras available to it, or even the ham TV system. Where we could capture pictures and use that either for ham TV transmission or for SSTV work itself.
I mean, even an astronaut with their iPhone transmitting it, swarms of beliefs on PD120 into the microphone.
Yes, it would, but
I know there are programs.
yeah, but we hit the good old problem of astronaut time and scheduling that time to be able to do that. At the moment, we've been pretty successful in getting astronauts just to as they go past the crossband repeater at the moment, just pick up the mic and start talking, and that's been very successful. But getting them to do anything else over and above that is a pretty tough job at the minute.
Any more questions? Okay. Well, that closes proceedings for today, but we've got another day tomorrow. Just a couple of housekeeping things. One, for those attending the dinner, it is 7:30, and the restaurant have asked us to be in the bar at 6:45. I'm looking around here and thinking that's not going to be a problem for some of us. If you give us a few minutes to rearrange the room, we will have the AMSAT-UK AGM.